Good morning, everyone. Good evening, good afternoon, wherever you are. Welcome to the first block of our parallel session on black hole thermodynamics. As you know, black hole thermodynamics has been around for about 50 years. And these last 50 years, according to Google Scholar, people have written about 10,000 papers directly related to black hole thermodynamics. I'm sure there are many more which are indirectly related to this field. So this means that it's a very active field. And so this time we are together here to share the last results from different groups, from different countries. And I'm very happy that we have people from many countries around the world. And so let's hope to have a very nice meeting, to enjoy the talks. And so let's start with David Kubisnak from the Perimeter Institute. And he will talk about thermodynamics of ADS black holes, central charge criticality. So welcome, David. You can start right now. Thank you.
Thank you so much, Hernando. Can everybody hear me? Yeah. Okay.
Yes, fine.
Very good. And thank you so much for inviting me to talk here. So my plan of the talk is to first review some generic features of thermodynamics of ADS black holes, and what is very characteristic and what is different in ADS to what happens in asymptotically flat case. And then I will concentrate on a simple charged example, considering just charged ADS black hole, or if you want, Reisner-Nordström ADS black hole. And I will review its critical behavior in various thermodynamic settings. I will mention phi Q criticality and PV criticality, and we will see what it means. I will also mention some additional results that follow from black hole chemistry for more complicated black hole spacetimes than just the charged ADS black hole. Then I will turn to holography and formulate extended first laws. So I will start from the CFT first law, the original one, and then I will derive the corresponding bulk first law. And we'll see that the bulk first law can have mu C term, where C is the central charge of the CFT, and mu is the corresponding thermodynamic variable. And then I will show you how this actually modifies the picture for charged ADS black holes. So my talk is based on two papers. One is quite old, goes to 2012, and that one is basically something like birth of the black hole chemistry. I will mention what black hole chemistry is in a minute. Whereas the second one is actually sort of like farewell to black hole chemistry, and I will try to explain what this means and why this is so. All right, so let's jump into that, thermodynamics of ADS black holes. So as already Hernando mentioned, black hole thermodynamics has been with us for 50 years. It started as an analogy between the classical laws of black hole mechanics and the laws of thermodynamics. However, this analogy was just simply too good to be not to be true and not to be taken seriously. And so the actual correspondence was actually established by Hawking in '74, when he showed by using quantum field theory in curved space that when quantum effects are taken into account, black holes, which are classically at zero temperature and there's no thermodynamics at all, when quantum effects are taken into account, black holes do radiate particles, and this radiation is approximately black body. So in particular, if you have surface gravity for the black hole, then the corresponding temperature is given over here. And then if you have the area of the horizon, then and measure it in Planck units, that gives you the entropy of the black hole. So in particular for Schwarzschild, you see that the surface gravity or the temperature goes like 1/m, and and the entropy goes like the horizon radius squared. So more generally, then for Schwarzschild, you can write down the following first law of black hole thermodynamics for ADS black holes, and the following SMAR relation, which is also in thermodynamics known as Gibbs-Duhem relation. So basically, the first one is a relation between the differential So you throw something in the black hole, and you are asking what is the response of the black hole, how the mass changes, how the charge changes, and so on. And the second one is like an integrated version of this. So it's like one equation between all these charges over here. So you may notice that I have included this, VDP term here, which is the crucial for black hole chemistry. And that basically, the P is related to the negative cosmological constant of ADS. According to this, we have negative cosmological constant minus that, so that gives you the positive pressure. And sometimes I will parameterize this cosmological constant in terms of the ADS radius L over here. So now, if you don't like varying cosmological constant, that's absolutely fine in the first law. You can just forget about this term over here. On the other hand, you cannot forget about the PV term if you consider the integral version of this. So for smart relation, if you do not consider the PV term, then there is no equality here, right? And so what is very interesting is that the two relations are related by the dimensional scaling argument, the Euler scaling argument. And so if you don't consider the variation of the pressure in the first law, then this term does not appear here. And so this equation is not true. So from a practical reason, you should be varying cosmological constant in the first law, so that you get a consistent smart relation over here. So anyway, so what is particular about ADS black holes is that they can be in thermal equilibrium with Hawking radiation. They exhibit interesting phase transitions, and they also provide the description of CFT at finite temperature via the ADS CFT correspondence. So none of these are necessarily true if you have just asymptotically flat black holes. They are typically the specific heat is negative, so they cannot be in thermal equilibrium. The phase transitions are not so interesting, and of course there is no well-established correspondence with some kind of quantum field theory. All right, so just to give an example, let me mention this most famous Hawking-Page transition, which goes to 83. And so what I'm plotting here is the free energy of Schwarzschild ADS. So the free energy is just mass minus Ts versus the temperature. And this is for fixed cosmological constant. So then you get a graph like that. So the radius of the black hole increases. So you have very, very small black holes over here. And then the radius increases. And there's a cusp here. And it goes down over here. And you have large black holes over here. So now, of course, according to the laws of thermodynamics, you should be minimizing you should be finding the global minimum of the free energy. And so you immediately see that the large black holes should be more stable or more interesting thermodynamically than the small black holes. And this is in particular confirmed by the fact that the specific heat here is negative, but specific heat here is positive. However, having just the black hole is not the whole story. You also have the Hawking radiation. So you can have an ADS space fill this radiation at a given temperature. So now if you calculate the free energy of this radiation, it is approximately equal to 0. So then you are basically looking at the system radiation plus black hole. And so you always want to find the global minimum of the free energy. And you see that in this region of temperatures is the radiation, which has the lower free energy than the black holes over here. And in fact, there are no black holes over there at all. And then over here, it's the black holes that have the minimum free energy. So what it tells you is that there will be a phase transition from radiation to large black holes. And because this thing is smooth, well, it's continuous, but it's not. The derivatives are not. There will be a first order phase transition at this T Hawking page. And of course, this okay. So this was for given pressure, but now you can vary the pressure, and so the whole picture looks qualitatively similar, but it just moves to different temperature. And so what happens is that you can draw the corresponding PT diagram. So for given pressure, I find the T Hawking page over here, and then I change the pressure, and I find another T Hawking page over there. And so you basically create like a coexistence line of this first order phase transition between radiation and large black hole. So now, according to Witten, this corresponds to some kind of confinement-deconfinement phase transition for the dual CFT. So you have the radiation, which would be the confinement phase, and then as you increase the temperature, you would confine the quarks. Of course, you can also look at this from the fluid interpretation, and then you have the infinite coexistence line over here, and so it would be like a phase transition between solid and liquid over here. So this will be a solid phase, this will be a liquid phase over here. Okay, so you see, black holes are very interesting already at, if you consider Schwarzschild ADS, and no charges, no rotation, no nothing. So now let me move to something slightly more complicated, and that's basically adding the charge to the black hole. And so I'll just be considering charge ADS black hole. This is the standard Reisner-Nordstrom ADS. These are the basic thermodynamic quantities. They are super simple. This is the corresponding free energy, M minus Ts. You can calculate the volume from the SMAR relation or from the first law, it doesn't matter. So anyway, these quantities satisfy both SMAR and the first law. So now people look at this already in '99, and it was the ADS CFT people like Chambly, Emperan, Johnson Myers, and also Svetic and Gupser. And so what they observed is that, let's consider the phi q plane, the electrostatic potential, and then the charge plane. And then let's plot the isotherms. So what is really plotted here is beta, which is 1 over temperature. But this is a T equal to constant line, and that's another T equal to constant line, and so on. So now you see that there's a certain critical temperature, beta C, where you see an inflection point. So above this, it makes weird shapes, but there's no inflection point. But then below this critical temperature, or below this critical beta, suddenly you see some kind of oscillations, and this looks like a Maxwell equal area law for normal fluids. So you would expect that at beta C there is something like a critical point, and below that there will be first order phase transition according to Maxwell's equal area law. And of course, this happens only for charges which are smaller than Q critical. So if you are above Q critical, there's no inflection point or nothing like that. But if you are exactly at this critical point over here, that gives you the Q critical, and below that you should see these oscillations and these phase transitions. And this is precisely what happens. So here's the corresponding phase diagram. So you have, for critical charges smaller than Q critical, well, Q critical, you have critical point, and then below that you have first order phase transition. And this will be a first transition between small black holes and large black holes. And you can see it from the free energy. So again, if you plot the free energy here, so you have small black holes here, and then the black holes the size increases like that. But of course, you always want to globally minimize, so you go to the bottom of the swallowtail. And so at this point over here, there will be a first order phase transition. You go down here. So it's a transition between small black holes and large black holes. But in this plane, phi q plane, it's a good plane for ADS CFT correspondence because you can do it exactly on the CFT side as well. But from the ADS point of view, it's not very nice, because if I have a fluid, van der Waals fluid, say, then the temperature is compared to 1 over temperature, which is a little bit strange. And then the pressure of the fluid will be compared to the charge, which is even stranger because pressure is intensive quantity, whereas charge is an extensive one, and so on. So there's an analogy, but we were not quite happy with this analogy. And so we looked at this analogy again from the PV point of view. So let me just remind how the standard van der Waals fluid works. So this is the van der Waals equation. So you have the pressure, volume, and the temperature, but you have also 2 parameters, A and B. And so A measures the attraction between particles, and it's positive, and B corresponds to the volume, to the effective volume of fluid particles. So you have to subtract that. And so you observe oscillations like that. Of course, there will be an inflection point, which is not plotted here. But these oscillations basically you replace by Maxwell equal area law, so that this area is equal to that area. And then you have a phase transition from liquid to gas. And the critical point is characterized by this 3/8 ratio. So now if you do the same thing for ADS black holes, the equation of state is not exactly the same as van der Waals fluid, but interestingly, the critical point is exactly characterized by the same ratio, if for this volume, if you define this volume correctly. All right, so now we have a phase transition between small and large black holes in the PV plane. And here's the corresponding comparison of the free energies. Now you see that they are very analogous. So this is for the black hole case, and this is for the van der Waals case. You can also plot the corresponding phase diagrams, and you see that the analogy is very complete. So you have small black hole, large black hole phase transition. This is in the PET plane, so lambda T plane. And so this is the standard van der Waals fluid. So small black hole will be something like liquid, and large black hole will be something like gas. So now, of course, you can play with various things over here. So for example, you can study the shape of this coexistence line, and that's given by the Clausius-Clapeyron equation, and you can compare it to what happens on the van der Waals side. You can also study the properties of the critical points, such as N-Fest equations, or the critical exponents around for this critical point, and you will find that there's both cases have mean field theory critical exponents, which are over here. So this basically suggests that the two systems are in the same universality class, and they should be the same systems, or whatever. Right. So now this was just for the charged case, but the PV thing, including the lambda in the first law, is very fruitful, and it leads to this new discipline of black hole chemistry. And so if you consider more complicated black hole spacetimes, you get more interesting phase transitions. So for example, this one is for rotating black holes in 6 dimensions, I think. So you see that now I have 2 critical points, 1 critical point, 2nd critical point, and then I have the first order phase transitions connecting here, and then I have where they meet, there's like a triple point over here. And this is very analogous to solid liquid gas phase transition, for example. You can also discover other things like isolated critical point, which I have never seen. It's basically like you have one swallowtail coming from here, and then you have another swallowtail coming from there, and they merge at the same point. And this is the point over here, and that point is called isolated critical point, and it's characterized by some interesting critical exponents and stuff like that. You can have reentrant phase transitions. I don't have time to explain what they are, but you can have superfluid phase transitions and so on. So black hole chemistry has been very, very fruitful. Moreover, using this PV thing, you can also look at the thermodynamic geometry and look at how the critical points you discovered through this PT thing are characterized by singularities of the corresponding thermodynamic geometry. And this is works which start by Ruppiner, Weinhold, and Hernando was involved in this. So for example, the proposal over here is, well, let's calculate the Ruppiner geometry, thermodynamic geometry, let's calculate the corresponding scalar, and this should give you the correlation length to the appropriate power, and so you can read off what this critical exponent nu is over here. Okay, so that's been very fruitful. Anyway, so to summarize the black hole chemistry, by doing this PV stuff, you discover very rich structure of phase transitions. The thermodynamic pressure, or the lambda, is actually plays a role of the control parameter. So really, if I change lambda, it changes qualitatively what's happening with my system. So if I have large P, there is no phase transition. If I have P here, I have 1 first order phase transition. If I have P over here, I have 2, and so on. So it's really the P which changes qualitatively what's happening with the black hole. It's the lambda. But then, of course, this leads to an interesting question: is like, what is the VDP really corresponds to the dual CFT side? After all, we are doing ADS black holes, and they should be interesting from the CFT point of view as well. All right, so let's go to the boundary correspondence, and so this has been a long way to understanding what's really happening and what this VDP corresponds to, and it all started with these papers over here. And so what they were basically proposing is that varying the cosmological constant in the bulk should correspond to varying the number of degrees of freedom, let's call them n, of the dual CFT. So there's so the cosmological constant is proportional to n to some power. So in particular, for the n equal to 4 SUN super Young-Mills theory, you find the relation that the ADS radius L is proportional to n to 1 over 4, where n is related to the central charge of the dual CFT by this relation over here. So C is something like n squared. It counts the number of degrees of freedom squared. And then what was proposed in these papers is that this VDP term really should give you something like mu dn term on the CFT side. So you have to basically change the CFT. You vary the number of degrees of freedom of the CFT, and then mu is the corresponding chemical potential. So this was the proposal, but this proposal is not completely right. And the reason is very simple, is that by changing the ADS radius L, you not only change the number of degrees of freedom, but you also change the volume of the CFT. And so this was well understood by Kark and Robinson, and also by Manusvisser in these two papers. And the reason is very simple. So let me just choose a simple slicing of our ADS black hole. So let's look at the asymptotic behavior. So large R. So so I start with some finite R here where I have the black hole, and then I go with R to infinity where the CFT lives. All right, so I do large R expansion of my ADS black hole metric, and you get something like this. And so then what you do is that you are at the boundary, so you set R equal to constant if you want. So this term is gone, but then you are also, because you talk about CFT, you are allowed to do conformal transformations. And so what people do is that they conformally rescale the metric, so they multiply by L over R square. And then this is the metric on the boundary, which is the standard metric on the boundary for ADS black holes. And so you see that there is an L square standing in front of the spatial part of the metric, and that gives you that if I had some volume, then the volume scales. So there's d minus 2 dimensions to your CFT. So this is how the volume scales with the cosmological constant, right? So really the volume of the CFT changes as you vary the cosmological constant in the bulk. All right, so now, having understood that we have basically both. We're changing the number of degrees of freedom, but we are also changing the volume of the CFT. One can formulate, as was done by Manusvisser this year, the most general first law for boundary CFT. And so this is the law, so that's the CFT energy and then TdS term, but then you also have the PdV term, where P is the pressure of the CFT, and V is the corresponding volume. And then you have the standard work terms, phi q and omega j. But then you also allow for variations of the CFT degrees of freedom. So there's this mu dc term, chemical term over here. So interestingly, having this first law, you can now apply the Euler scaling argument, and that gives you what the P has to be. So this is this first smart relation, and gives you that P is just E over V. And then you can look at how various quantity scales with the central charge. And that gives you this other smart relation over here. So you have two smart relations, and you have this very, very general first law for the CFT. Very good. So now you want to relate this very, very first law of the CFT to the bulk. And how you do it is that Manus proposed this very general thing. So you have the central charge is related to the lambda and g over here, and then k is some coefficient which depends on the particular CFT. You also have the standard dictionary over here that the energy of the CFT is the mass in the bulk, and then the charge rescales with g and l, so that the q is the standard bulk charge and phi is the standard bulk chemical potential or electrostatic potential, right? So now I use these relations here, and I rewrite this first law. And one way to do it is that you just arrive at the first law, which suddenly has not only variable lambda, but also variable g. So if you really want to take the CFT side, seriously, you have to vary not only lambda, but also you have to vary the Newton's constant g. Of course, people, well, from bulk perspective, this is a little bit crazy, but from the CFT perspective, this is what you have to do. Of course, when you fix G, then you return back to our favorite black hole chemistry, and that just becomes P, and this is the corresponding thermodynamic volume. All right, what we also did is that we basically changed this. We used the relation for the CFT here, and we differentiated that, and we basically replaced the term with G to the term with the central charge. So this is the new first law. It's like sort of like mixed first law, where you have this term corresponds to the CFT side, and the rest is just purely bulk. But what it certainly allows you to do is it allows you to study the bulk thermodynamics at fixed central charge, but of course the price you have to pay is that both G and L vary. And you have the new thermodynamic volume over here, which is over there. And so this is the new first law. So let's see, how this new approach basically changes the criticality of the charge radius black holes. So now your free energy is still m minus Ts, but now it depends on the central charge, which you can fix. And so you still get the swallowtails as you would before, but before you got these, variations, like you got the swallowtail or no swallowtail, depending on the pressure, depending on the cosmological constant. Now, interestingly, the pressure does not matter at all. It's just, if you change pressure, and you start, let's say, with the swallowtail, you just get a small swallowtail, but qualitatively, the behavior does not change. What matters now is the value of the central charge, the number of degrees of freedom of the CFT. So there's a critical central charge when you have the critical point. If you have larger number of degrees of freedom, you can have a first order phase transition. If you have smaller, you don't. So this is completely basically destroying the whole black hole chemistry. It's just, the pressure does not matter anymore. It's the central charge which matters. So you can see it also in this diagram. So, this is plotted for various pressures. You see that, there's always one value of the central charge. This is 1 over C. So for large number of degrees of freedom, you have a first order phase transition here, and there. So it's only, the details change, qualitatively change, but quantitatively they don't change depending on the pressure. So only when the CFT has large number of degrees of freedom, the bulk black hole can experience a phase transition. All right, let me just very briefly mention the corresponding chemical potential to C. So this is the general formula, and you can plot it for charge radius black holes, and it, for example, looks like this. Or if you are below critical center charge, above that, then you have these very interesting wiggles over here. But what is interesting is that in classical thermodynamics, the chemical potential has to be large and negative. So this would be like a classical regime over here. And where the interesting stuff happens for radius black holes is like a quantum regime. So anyway, I'm running out of time, so let me summarize. So I hope I convince you that ADS black holes are very interesting from a thermodynamic perspective. They can be in thermal equilibrium, they demonstrate various phase transitions, they characterize the behavior of the dual CFT. And in particular, I focus on charge ADS black holes, which sort of show like something like van der Waals criticality. And this was uncovered a long time ago in the phi-q plane, but the analogy was really complete in the PV plane and in the approach of black hole chemistry. So if you are interested in black hole chemistry, this is the review, and so you can look at the review and our citations of the review. However, if you just vary lambda, then it corresponds to both varying the central charge of the CFT and the volume. So you have, it doesn't correspond, right? So you need two quantities over here to vary in the bulk if you vary two quantities on the CFT side. And so to amend that, you also have to vary the gravitational constant, as you will see. But the way how to do it is that you start from the CFT first law, which is the general one, the most general one. And that translates to varying both G and lambda in the bulk. Or if you like, this mixed law a little bit better, which corresponds to some kind of thermodynamic ensemble, then you have this this first law over here. And so this allows to study thermodynamics of bulk black holes for fixed CFT central charge. And what is very interesting is that all what we learn about in black hole chemistry, that the pressure is important, is no longer true. It only what is only interesting is the value of the central charge. The P is just a spectator and doesn't change qualitatively what happens. So in other words, black hole chemistry becomes CFT chemistry. Thank you so much.
Thank you very much, David, for this very nice talk. So we have some time for questions. If somebody has a question, just go ahead, switch on your microphone and ask the question. I don't see any raised hands. Okay, let me ask you a short question, David. Okay, from the point of view of CFT, it is necessary to variate G, the gravitational constant. So from the point of view of black holes, Do you have any possible interpretation?
I think this is a very good question. Thank you so much for that. So if you are looking at this extended first law, CFT first law, right? So what would people, traditional CFT people, what would they do is that they would just write TdS here, phi dq, and omega dj. They wouldn't consider the possibility of changing the CFT volume, and they wouldn't consider a possibility of changing the central charge, right? So in that case, of course, you can do the thermodynamics in the bulk, which would be just, I fix the central charge over here, I don't vary the lambda, so this term would be gone. And then I would just have correspondence between the standard first law in the bulk and the standard first law on the CFT side. However, what people have been doing, and unfortunately or fortunately, I initiated that as well, is that people have been playing with the idea that the cosmological constant can vary in the bulk, and maybe not necessarily the cosmological constant, but there are ways how to vary the cosmological constant, like effective one, for example, with you can use subscalar fields and then consider the effective cosmological constant as the value of the potential of the scalar field and so on. Or you can put some four forms on your space. And so there are ways how to effectively vary lambda. So then people were questioning, like, what happens on the CFT side, right? But once you start varying lambda, you necessarily led to varying central charge, but also varying the volume over here. So you have to vary both. But then, varying volume and central charge induces that you also have to vary G back in the bulk. So I would say the answer is you either don't vary anything, so you don't vary lambda, you don't vary gravitational constant, and you fix the volume of the CFT and you fix the volume of the central charge, or you have to do both. You have to vary this one, and this one, and that one. So now what is the interpretation? I don't know. I quite like the idea from the CFT point of view that you are working at a fixed central charge. After all, people don't like changing, the value of the number of degrees of freedom of the CFT or the central charge. But it's very natural to vary the volume of the CFT on the boundary. So if you just start varying the volume of the CFT on the boundary, you are left to varying, both things here in the bulk as well. So I don't know what it corresponds to the bulk. It's certainly interesting and future study. But people have been considering variation, varying gravitational constant in the past. But definitely that deserves more attention, I think. Sorry, it was a simple question and I answered a very long way.
It's a very good answer. Very good. Thank you. Okay, thank you so much for your talk. Now we will start with the next speaker, with Simon Boudet. Simon.
Yes, hello.
Okay.
Okay, can you see the slides?
Yeah, very good.
Okay.
So you can start.
Okay, thank you. And good afternoon, everybody, or good morning. I'm Simon Boudet, and in this talk, I will report an analytical hairy black hole solution we found in a model of modified gravity. So I will first briefly introduce the model, the gravitational model we've been working on. Then I will present you the analytical hairy black hole solution, and then I will show you how we computed the thermodynamic quantities of interest for this black hole, that is the energy and entropy. And finally, I will end with a discussion on the thermodynamic stability and the superentropic nature of this black hole in the context of the extended phase space approach. So let us start with the gravitational model. And the starting point here is the Holst action, which is a modification of the Hilbert-Palatini action of general relativity. So we are in a first order formalism in which the metric and the connection are considered a priori as independent variables. And we include an additional term, the Holst term, in the action, which is multiplied by the so-called Mirzi parameter, gamma 0. Now, in this work, we followed an idea proposed in literature in which the Mirzi parameter is promoted to a fundamental field gamma of x. Now, this was originally motivated by the attempt to address a quantum ambiguity, which is present in loop quantum gravity, whose quantum implementation in turn can be derived starting from the Holst action. However, afterwards, gravitational models featuring this immersive field have been extensively investigated in several different contexts, such as cosmology, gravitational wave physics, and in connection with the CP problem. But however, there seems to be a gap in literature concerning the possible effects of the immersive field in black hole physics. And the main reason being the existence of no-hire theorems, which make the search for analytical black hole solutions with non-trivial scalar fields particularly difficult. So this was the reason why we got interested in this work. And in the following, we will consider indeed a model featuring this immersive field, including also its own potential term, WF gamma, but within a more general f of r-like framework. So we include also an f of r-like modification of the Holst action. Now here, the potential is included by hand, but there is actually a more natural way to generate an interaction term for the immersive field. And I will talk about this in another parallel session on Friday. And once given this gravitational model, we, of course, in the following, specialize to vacuum spherically symmetric configurations and look for black hole solutions with a non-trivial radial profile for the immersive field. Now, since we are interested in the in analytical solution, it is convenient to first re-express the theory with two successive steps. The first one consists in the transformation to the Jordan frame, which can be done defining a new scalar field phi in terms of the derivative of the function f with respect to its generic argument, and introducing its own potential term v of phi defined in this way. And with these definitions, the action reads in the Jordan frame like this. Then the second step consists in first solving the equation of motion for the independent connection, and then substitute back the result into the action in order to work with an effective second order scalar tensor theory, in which the only dynamical degrees of freedom are the scalar fields and the metric tensor. And here, just for convenience, we reparameterize the immersive field in terms of this new scalar field psi, while the scalar field phi is the same as before, and we note that it is in non-minimal coupling with the metric tensor. Now it is easy to compute the field equations for the metric and the immersive field, while the field equation for the scalar field phi can actually be recast in the form of the so-called structural equation, from which we see that phi is not an actual independent dynamical degree of freedom. So this is not a differential equation, being instead really algebraically related to the immersive field via the solution of the structural equation. Okay, so in order to proceed, we selected a model, a general quadratic model with a cosmological constant term, where the parameter alpha rules the quadratic correction. And with this choice, one has this expression for the scalar field phi, which turns out to depend on the potential of the immersive field, which, in order for the solution I will present shortly to actually satisfy the equations of motion, we have to choose a posteriori given by this expression, where psi0 is another constant. Okay, so I will now present you the black hole solution, and let us start with the metric tensor, which describes an asymptotically anti-de Sitter black hole with hyperbolic horizon. So this sigma here is the line element of a two-dimensional submanifold, which has a negative constant curvature. So the horizon of the black hole will have hyperbolic topology, which is something allowed by the non-trivial anti-de Sitter asymptotics of space-time, which can be seen looking at the asymptotic behavior of the metric function h, where L is just the anti-de Sitter radius. And finally, there is an overall conformal factor, omega, which depends on the parameter alpha and on the parameter m, which the mass parameter m, which we will see is related to the mass energy of the black hole. Now, beside the origin, there are two other curvature singularities, which are located at the roots of the conformal factor omega, but these can always be hidden behind the event horizon located at RE, provided that the mass parameter, or equivalently the horizon radius, are greater than those two critical values. And moreover, we also restrict ourselves to the positive branch for the alpha values, since for negative values of alpha, a naked singularity can always appear. Okay, and with this, beside the metric, there are the scalar fields, which have a non-trivial radial profile shown here, which is regular on and outside the horizon. And let me note that for alpha and psi0 equals 0, this solution reduces to a previously known solution, the Martinez-Troncoso-Zanelli black hole, where, however, there is only one scalar field, and moreover, it is minimally coupled to geometry. While here, for alpha different from 0, we are in the more general situation of non-minimal coupling. Finally, let me note that asymptotically, the scalar fields, the immersive field goes to a constant gamma 0, and the scalar field phi goes to 1. So asymptotically, we recover the standard picture of a constant immersive parameter, while in the proximity of the black hole, the mass energy of the latter can actually excite the immersive field, which possesses a non-trivial radial profile there. So having found this solution, we proceeded further, studying its thermodynamic properties. And we did this employing Euclidean path integral methods. So one first performed a weak rotation to imaginary time tau, yielding the Euclidean metric. And then one can compute, as usual, the thermodynamic partition function via a saddle point approximation centered on Euclidean on-shell action, I of beta, where beta is the inverse temperature, and it turns out to coincide with the period of the Euclidean time tau. So eventually, its expression is given by this equation, from which we see that in order to guarantee the positivity of temperature, the horizon radius must be greater than this critical value, which is the same condition we imposed before in order to avoid naked singularities. Then once the partition function is known, one can compute the thermodynamic quantities of interest via applying the usual thermodynamic relation. Okay, so let's turn the attention to the actual computation of the Euclidean action, which we perform in the Hamiltonian framework. So here we perform the Legendre transformation, and it's just the lapse function. H is the Hamiltonian, which of course vanishes on shell, while we also computed the integration over the two-dimensional submanifold with area sigma and the Euclidean time with period beta. Here you see we included a boundary term, whose role is twofold. On one hand, is needed in order to have a well-posed variational principle, so it acts like a Gibbons-Hawking-York-like boundary term. And on the other hand, it is needed to cure divergences of the action, of the on-shell action, due to the anti-de Sitter asymptotics. So the expression for this boundary term can be computed imposing that the non-vanishing boundary terms coming from the variation of the bulk action precisely cancel the variation of the boundary term. So this yields the expression for the boundary term at infinity and on the horizon, where here in the last step, we just consider that sigma omega r squared computed at the horizon is the area of the horizon. And we recall that phi is actually related to the immersive field via the solution of the structural equation. Now, since H equals 0 on shell, the only contribution to the Euclidean action comes from the boundary term. So this is the final result, from which we compute the mass energy of the black hole, which we see it's related to the mass parameter m, and the entropy, which we see it's modified with respect to the standard area law. And the correction here depends on the value of the immersive field at the horizon. Now, let me note that had we started from the very beginning with a constant immersive parameter, then we would end up with an expression for entropy satisfying the usual Bekenstein-Hawking formula. Okay, now what I want to say is about the boundary term, which here we just we did not use in its full explicit expression, but actually the same results we obtained before can be obtained starting from this action, where we added these boundary terms, which are shown here in their explicit covariant expressions. And the first one is a Gibbons-Hawking-York-like boundary term, generalized to the case of non-minimal coupling, where K is just the extrinsic curvature of the boundary, while the other counter terms are those needed to cure the divergences of the on-shell action. And here we used in literature, we're known for the case of a minimally coupled scalar field, which can be derived from this one, simply setting phi equal to 1. While here we use the suitable extension to the case of a non-minimal coupled scalar field. And moreover, we can note that the last counter term, it depends on the immersive field. And this is due to the to the fall off at infinity of the immersive field, which is lower than that of standard localized distributions of matter. And this causes a back reaction on the metric. And this feature has to be taken into account when regularizing the on-shell action. So this is why the last term depends on the immersive field as well. Okay, so let me end with a discussion on the thermodynamic properties of this solution in the extended phase space approach. So in this approach, as we saw in the previous talk, one considers a pressure term due to the presence of the negative cosmological constant, together with its conjugate quantity, a thermodynamic volume, which can be derived via this thermodynamic relation, the first law. And it turns out to be given by this expression in our case. Now, this volume, this thermodynamic volume, does not always coincide with the geometric volume, and therefore its properties have been extensively investigated in literature. And in this reference, this conjecture was proposed, the so-called reversive supersymmetric inequality conjecture, which states that apart from these numerical coefficients, this ratio between the volume and the area of an anti-de Sitter black hole must be greater or equal than 1, where the equal sign holds for the simple Schwarzschild anti-de Sitter solution. So the physical interpretation is that all anti-de Sitter black holes must have an area and therefore an entropy which is smaller than the one a Schwarzschild anti-de Sitter black hole would have for the same value of the volume. Now, this inequality was first motivated by the observation that all known solutions seem to satisfy it. But then afterwards, some solutions were found violating the inequality. And if this quantity I can be smaller than 1, then one can have a greater area and therefore a greater entropy than the bound, than the maximum value saturated by the Schwarzschild anti-de Sitter solution. And this is why these solutions were dubbed superentropic black holes. So we check this behavior in our case, that is for in dimension 4 for k equal -1, so for hyperbolic topology of the horizon, and unit surface of the latter equal to sigma. And it turns out that the inequality is violated in almost all parameter space, and therefore the black hole is superentropic. Now, these superentropic solutions have been shown in these two references to possess negative specific heats, signaling a thermodynamic instability. And it was proposed this conjecture which states that all superentropic black holes must be thermodynamically unstable. So we checked the stability and we computed the specific heats at constant pressure and volume. And while the former is always positive, the latter becomes negative at high enough temperatures, signaling an instability. And therefore, our solution seems to be to support this recently proposed conjecture on the instability of superentropic black holes. Now, I have to say that very recently a superentropic black hole was found, and it was shown to have both the specific heats positive. So it seems to violate this recently proposed conjecture. Okay, let me end with some concluding remarks. So I've shown you an analytical black hole solutions where the scalar hair are provided by the immersive field. And we computed the entropy, and its expression turns out to depend on the nature of the immersive field or parameter. Indeed, in the case of a dynamical immersive field, the entropy is modified with respect to the standard area law, while in the case of a constant immersive parameter, the usual Bekenstein-Hawking formula holds. And this could, in principle, allow to discern between a constant immersive parameter or a dynamical immersive field. Then I've shown you how the reversive supersymmetric inequality is violated for our solution, and therefore the black hole is superentropic. And we computed the specific heats, and these are negative. One of these is negative, and therefore our solution is thermodynamically unstable in support of a recently proposed conjecture on the instability of superentropic black holes. Now, let me end saying that even if recently a solution appeared violating this conjecture, it could be interesting in the future to investigate the thermodynamic stability of these solutions via more sophisticated non-extensive methods, which have been shown in literature to yield results on the stability of black holes, which are not consistent with the results one obtains simply looking at the signs of the specific heats. So investigating these, the stability of these solutions could give, via these methods, could give different results on the thermodynamic instability of superentropic black holes. And that's it. I thank you for the attention.
Okay, thank you, Simon. Very nice talk.
Thank you.
So we have some time for questions. Just switch on your microphone and ask the question.
Maybe can I start? Okay, Simon, very nice talk, very nice talk. So maybe can I have just a few questions? So first you mentioned that if you set the gamma equal to constant, then you basically don't recover any corrections to the entropy. Is this the general case, or is it just valid for your black holes? Because, for example, if you add, I don't know, Gauss-Bonnet term, which is also topological, you can change the value of the entropy by a constant or something like that. So what about your topological term? Is it?
I don't know about the Gauss-Bonnet case, but here actually the term we add is not topological. So the Holz term, I don't know if this matters, but the Holz term here is not a topological term. It just vanishes on half shell, we say. So when the just the equations of motion for the connection are satisfied, and this is because of the Bianchi identity simply. But I don't know what you're asking. If
no, I'm just surprised that it doesn't, doesn't contribute to the entropy. That's all.
yeah, of course. Yeah, I think it's just the reason why it does not contribute is that for a constant here, you actually recover on shell standard F over Palatini gravity. So the correction disappears. It's different from the topological term because in that case, it does not affect the equations of motion at all. In this case, it is vanishing on shell. So in the case of a constant gamma, of course, while if gamma is not a constant, you don't get this the vanishing of the additional term, and therefore it implies a modification.
Okay, thanks. Maybe second question. So you said you went to the Jordan frame, so you basically did some conformal transformation of the metric. I guess to recall that can actually change thermodynamics of the system, but I'm not sure. Have you thought about that, or? Yeah.
So actually, we do not perform a conformal transformation. So you could do that. So here the transformation to the Jordan frame is only performed defining these functions, and then you can check that on shell it is equivalent to the previous action. But there is no conformal transformation of the metric here. You could do this here, defining a new metric G tilde equal phi G, and then you would have that the new field phi in the new frame is minimally coupled to the metric. But we do not do this, and so there is no implication of this on the thermodynamics. But actually, I think that it has been shown that the entropy is equivalent, is a conformal invariant. I'm not sure about that, but I think that it does not change for maybe in some class of theories with some assumptions on the transformation, but
yeah, I just remember there were some papers where they claimed that it can change the entropy and stuff like that. But maybe
this is just the reason why we stick with the original frame, and avoid any conformal transformations.
And then just a last comment. So it was not Brian Dolan in 2013 who actually posted the reverse isoperimetric inequality conjecture. It was actually us 3 years ago, three years before that. So maybe you can find the reference with Cvetic. That's okay. Don't worry.
Okay. I will check if in the paper we did it correctly. I think so. There were multiple references. I'm sorry. Here I put only one, but maybe in the paper there is the correct one. I'm sorry.
Okay, any more questions? Okay, just a comment, Simon. Yes. I agree with David that actually a conformal transformation changes drastically the thermodynamics of the black hole. This is what usually happens, because actually we believe that a conformal transformation, if you go from the Einstein frame to the Jordan frame, everything changes. So the physics changes and also the thermodynamics. This is what usually happens. Just a comment.
Okay, thank you. Fortunately, we did not do. We did not perform a conformal transformation.
Yeah. Okay, thank you very much.
Thank you.
Thank you. Okay, we continue with our next speaker, who is Jiwen Wang. Jiwen is here, and you will talk about information recovery from evaporating black holes. So, thank you, Jiwen.
Hi.
Okay, yeah. Go ahead.
Okay, can you see my screen?
Yes, everything is fine.
Okay. One of the immediate application or implication of black hole thermodynamics is black hole information paradox. And there are lots of quantum way, try to solve this information paradox. But here, I will introduce a very short paper we just published, about based on one way to give some potential solution to this question. How one may recover information from evaporating black holes. Of course, the original evaporating should be caused by Hawking radiation, which is a quantum effect. And the co-author is Professor Sam Bernstein and Surya Das. Classically, a black hole, a very simple definition is, nothing can escape, if you don't consider Hawking radiation. And the no-hair theorem claim, a stationary black hole, can always be described by three very simple, physics parameter, which is the mass and the electric charge and the angular momentum of the black hole. And all the other, properties of the black hole, like the surface gravity of the black hole or the horizon area of the black hole can be expressed into these three parameters. This is some very basic things. And then, people discover black hole are thermal, the first people try to study this maybe is, Jacob Bekenstein, where, John Wheeler asked him, about the question that what will happen if you throw a cup of tea into a black hole. And after some study, Bekenstein claim or conjecture that, black hole should have an entropy which proportional to its horizon area. Then short after this, Bernard and Hawking found the follows of black hole mechanics. But until Bernard and Hawking discovered the follows of black hole thermodynamics, this is still an analog. The follows of black hole thermodynamics claim, you have a surface gravity which is a constant for stationary black hole, which is like the temperature. And you have a first law, you have a second law, and you have a third law, but until now, it's just an analog, which seems, the surface gravity may correspond to the temperature or related to the temperature, and the horizon area may related to the entropy. This become a more serious question when Hawking found Hawking radiation. He studied, the evolve of a quantum field, in a curved space-time with a black hole, and he found, you will find the radiation. You will find the black hole is radiate at a temperature which is kept over 2 pi. But that's 1 year after he published this very influenced paper. He found because the no hair theorem which claim a stationary black hole should be described as some very simple quantity of a black hole. So the radiation could be a very pure thermal radiation which contain very tiny information about the original matter which collapsing into the black hole. So when a black hole is totally radiated away, nothing will left, and all the information that about the matter that collapsing into the black hole is lost. This is the black hole information paradox, and lots of people use quantum aspect like quantum entanglement, which claim the two particles, one go to infinity and the one fall into the black hole, are entangled with each other, or some other like a quantum field theory to answer this question. But there is still not a totally agree solution. And here we try to give a potential solution or contribution to this question based on some very classical aspect or classical method. Before introduce our way, I will introduce the Penrose diagram for some very for the Schwarzschild black hole. In a stationary case, for Schwarzschild black hole, the singularity is space-like, and the horizon, is and the horizon is now, so nothing, nothing inside the black hole, can escape the black hole, can go to the outside the universe. And when you consider the black hole is evaporating away, for example, by Hawking radiation, this situation will not change. Information can still not escape from the horizon. Since for curl or rotating black hole, have a little change, because for rotating black hole, the R equals 1, is time lag, and if you connect two universe, which contain a curl black hole, information can go from one universe, to the other universe. This is a null radiation, which can go to another universe. But if you stay in our universe, you still have the information loss problem, because it seems the information can only go to the other universe, which meaning within our present universe we still have this information paradox problem. The first people try to use the classical way to give some potential solution to this question is Prick and Welzak. They chart the white hole. In their paper, they claim they chart the black hole, but they make a small mistake. I will talk about this a little later. In fact, they are chart the white hole, and they consider the black hole is evaporating, and they don't care, what caused this evaporating. Of course, you can just say, it's because Hawking radiation. So the mass of the black hole, or the charge of the black hole, is changing with time. And after some calculation, they found they proved that the black hole horizon, when the black hole begin to radiate or to evaporate, the black hole horizon will become time lag, and the black hole singularity will also become time lag. So the matter, since the horizon is time lag, this meaning information or matter following a null radiation can go outside the black hole horizon. This meaning the black hole, the black hole will decreasing with time. And there's a classical, since the black hole horizon is a timeless, this means even classical matter can go outside the black hole. So potentially, you know, there's a classical channel you can transform information from the inside of the black hole to the outside of the black hole. And all this is based on, you know, classical calculation. You just consider, you know, just assuming the black hole can evaporate. This is a short, you know, proof that the matrix used in their original paper, in fact, is a white hole. This is the matrix used by them, you know, this is the matrix used by them. And if you calculate the expansion for the null vector, you know, outgoing null vector, and this is an ingoing null vector, you will find, you know, the expansion that located the parent horizon, in fact, is the ingoing null vector, which means the horizon must be a white hole. Of course, you can also see this, you know, if we are very familiar with the matrix from the manner sign they use in the matrix. So this is a very small mistake, you know. They may just don't care, don't pay too much attention to this in their original paper. And we want to generalize, you know, this analyze, you know, to rotating charged black hole. The two reasons, you know, first is originally they in fact study a white hole. So maybe you do the analysis for black hole, things will change. The more important reason is because, you know, in fact, the black hole, you know, we can find in astrophysics or in the real universe, you know, is always rotating. So study rotating black hole must be more closely connected to the real black hole. So we want to generalize, you know, their analyze, you know, to rotating and charged black hole. This is the matrix we use, you know, and since it's a rotating charged Vedia type black hole, and since we are assuming the black hole is evaporating, you know, we require, you know, the mass and the charge and the angular momentum depending on the coordinate time mu. And to study, you know, the two-dimensional Penrose diagram, you know, for this rotating black hole, we restrict the matrix to the symmetry, you know, axis along, you know, theta equals 0. Since theta equals 0, you know, this meaning d theta equals 0 and sine theta will equal 0. If you look at equation 1, you will find, you know, since sine theta equals 0, all this term will vanish and d theta term will vanish. So this matrix, you know, on this axis or close this axis will reduce to something like this. And one can pull, you know, d mu out. And, you know, in fact, from here, you will already find, you know, this is quite like the double null coordinate. So without loose generatives, you know, we assuming, you know, MQ and the angular momentum A is proportional to each other and linear functions of the time coordinate mu. So the mass will change with the time, you know, by this function. And mu, you know, describe, you know, sorry, this is U. Mu will describe, you know, the decreasing, you know, rate of the black hole. When this is big, you know, it's decreasing very quickly. And all the other parameters that's proportional to the mass of the black hole. Then, you know, equation 2, this is equation 2. What we have pulled d mu out. Equation 2 will be right into, you know, something like this. We just insert this, you know, relation into the equation. We do nothing from here. And then we write this into a double null coordinates. But, you know, here, you don't know what is the function, you know, the pre-function j mu r is. We just know, you know, there's a function, there's a relation, you know, between these functions. So we need to calculate what j mu look like. There's a Euler relation provide a solution for this question, and so you can calculate it out based on Euler's relation with J mu r equals to this finally. And then from equation 6 and 7, you can find the relation. You can express y, the parameter, the coordinate parameter, y into partial v partial r and mu tutor. From here you can see the power in the r function is in r cubed. This means maximally there could be 3 singularity for this new coordinate system. So a complete coordinate may be obtained by connected different patch of the coordinates based on how many singularity you have. It's depending on this parameter value. We have detail analyzed in our paper, but I will not introduce here. And so now you have the double null coordinates. And we first study the space-time surrounding r equals 0. I may emphasize r equals 0 is not the singularity for the rotating black hole. This should be clear for everyone. And then we study the ds square surrounding r equals 0. We find when r approaches 0, this will always be minus, which meaning this is a time-lag pace or time-lag congruence around r equals 0. So, but more important, in fact, is the horizon. What will the horizon look like? It is a time lag, or it is now, or something, or some other things. So then we try to study what's the horizon look like at least rounding the axis theta equals 0. We first define a function as f mu r equals this. This is the apparent horizon of a rotating black hole, rotating charged black hole. It's just m plus and minus this. So in fact, this is just the label for the apparent horizon of the black hole for stationary case. For stationary case. So this function equals 0 just labels the location of the black hole horizon. But our study is time dependent. We study the time dependent charged and rotating black hole, and this is the solution for stationary case. So we need to solve the exact apparent horizon location. Use use the expansion way. By studying the expansion of the outgoing null vector and the ingoing null vector. After some study, we found the apparent horizon for the time-dependent case of the rotating and the charged black hole looks like this. This is just the horizon location for when when the space-time is stationary, when it is not time-dependent, and when we consider the time-dependent, in the linear case, we will find there's a parameter mu, as I described, as I introduced before. Mu describes how quickly the black hole evaporating, or the evaporating rate of the black hole. So in fact, mu could be very small, depending on how you, at least theoretically, depending on how you choose it, it could be very small. In fact, this meaning the shape of the horizon location, we can think, it could be infinitely small, based on how serious the black hole depending on time. So we can ignore this term when we do some quantity calculation. So and then we begin to calculate what's the horizon look like. Is it time lag or now or something or some other things. And we need first this function f mu equals 0, in fact defining a horizon tube. So and to find the normal of this horizon tube, we just take the derivative, the d derivative, for this function. which meaning we have a mu, how this function depending on mu and how it depending on r. And we will get a vector, it is not depending on the angular part, since we are studying a symmetry, axis. So after we have this vector, we can study, its magnitude. And finally, we will find it is an expression like this. This is, this part is always smaller than 1, and this is minus 1. So this meaning this part will always be minus. But mu, is the evaporating rate, which is a minus scalar. So this meaning this whole term is always positive. So the vector, normal to the horizon tube is always a space like this meaning. Yeah, it is the normal vector of the horizon tube is always space like this meaning the horizon tube is always time lag. So yeah, the horizon tube at least surrounding or nearly the axis, theta equals 0 must be time lag. So the summary of our technical result is the region immediately surrounding r equals 0 is time lag. So this part is time lag, and the apparent horizon at theta equals 0 is also time lag. Oh, in fact, our proof is for both the inner apparent horizon and the outer apparent horizon is both true. Of course, we care more about for the outside apparent horizon. So since the horizon is a time lag, this meaning if you have some matter or some information follow some null radiation, they can escape evaporating black hole. So when the black hole begin to evaporating, for example, it began to evaporate because the Hawking radiation, then the horizon will become time lag, and in fact more matter follow a null radiation or a path which is similar to a null path can escape the black hole, we think. Our result shows this. And yeah, so this is some implication of this technical result. The first one is that it seems there could be at least one classical channel, and we guess generalize to more to other places maybe should also be possible and easy, through which information can escape, and information can also recover from this channel. And this also meaning black hole maybe shrinks faster than purely predicted by Hawking radiation, because there will be some additional outflow which could be associated with matter. And the other important thing we may point out is there's a classical channel, and matter or information may escape from this classical channel seems. And all this matter or information is not thermal. We don't require, because this is not based on black hole based on the laws of black hole thermodynamics. So in fact, this information could be not thermal. It's just be normal matters. Seems like this. And yeah, this is the result of our short paper. Okay, thanks.
Okay, very good, Ji-Wei. Very clear talk, by the way. So we have some time for questions. Again, just switch on your microphone and ask the question. No questions. Okay, I have a very short question.
Yeah.
You use the concept of horizon tube.
But yeah,
Usually this is what people understand until horizon tube is the horizon which evolves in time, which is in the case of apparent horizons in cosmological models where you have an explicit dependence on time. What's in your case the coordinate which generates this tube?
It seems, we are more like, it's more like we are calculating a line in a horizon tube, which is labeled by, theta equals 0. And it's based on our double null coordinates, seems. I'm not sure whether I answer your question.
Yeah, this is somehow I don't understand the idea of the tube here. You see? Okay.
So maybe can I have a short question?
Sure.
Yeah. So I like this as a classical model, to explaining this problem. But of course, I guess it's just more a comment. But this seems just as a phenomenological model. But as far as I know, there is no theory which would support this model, right? So there's no it cannot be a theory of quantum gravity, or is it? Is it some kind of theory of quantum gravity which predicts this model?
I'm not. I don't think so. I don't think there's any quantum gravity theory to support this model. I guess it's just based on maybe general relativity. I guess most of the calculation.
Yeah, but the general relativity predicts a different picture, right? And so you have to start departing from general relativity very soon, and it's not even in the quantum regime, right? So I'm a bit puzzled. I like the model, but it seems like it's a model designed to explain, but it doesn't come from anywhere.
The effect, that your classical, black hole cannot evaporate, and the effect, in fact, you are assuming a black hole is evaporating is some quantum effect, in fact. It seems, we just assume, based on some, potential quantum gravity theory, black hole can evaporate, because, even until now, we don't have a satisfied, quantum gravity theory, so, but, in a semi-classical quantum gravity, which, when you merge, quantum field theory or quantum mechanics with general relativity to study black hole, it seems, like Hawking discovered, black hole can radiate things away or radiate Hawking radiation. So yeah, but maybe, someday when people find really, quantum theory of gravity, they will, naturally solve this question or explain this. But yeah, I know this is not a final, theory or final result. It's still far from that.
Yeah, that's fair enough. Thanks.
You are right. Someday somebody will do that. We'll find the quantum theory of gravity. Okay. Very good. Yeah. Okay, thank you very much, Jiwei.
Thank you.
So,
thank you.
We go to our next speaker.
Okay, thanks.
Shore. Shore, could you please share? Okay, very good.
So can you see my first slide?
Yes, we can see. Very good,
hello.
thank you. So, well, let me just say the title of your work, which is there, stress energy tensor for a quantized scalar field. So please go ahead, Shore.
I think I can't hear my voice. Oh, now it's good. Okay.
It's good. It's okay. It's okay.
Hello. Today, I'll talk about the computation of the stress energy tensor for a quantized scalar field when a black hole forms from the collapse of a null shell. This is a part of my current research work that I'm doing with in collaboration with Paul Anderson, Raymond Clark, and Alessandro Fabri. So why a semi-classical stress energy tensor? This is a very useful quantity that can give us information about the quantum effects in the curved space-time, such as the vacuum polarization or the particle production process. For curved black holes and static black holes, there has been some computations of the stress energy tensor, but in the case of a collapsing null shell, that is probably the simplest model for a collapse to form a black hole. There is no full numerical computation of the in vacuum expectation value of the stress energy tensor. Today, I will present a method that we have developed and that can be used to compute the stress energy tensor in the null shell space-time. And the results that we are working on that can be used to examine the late time behavior of this quantity. So first, I will explain briefly about the collapsing null shell model, and then talk about a scalar field in the null shell space-time. And next, I will talk about our method that can be used to resolve some problems involved in the computation of the stress energy tensor, such as the renormalization process and the computation of the in-modes. And at the end, I will provide some tests that shows that our method will work. In the collapsing null shell model, a spherical symmetric null shell collapses and form a four-dimensional black hole. So this is the Penrose diagram of the null shell space-time. The blue dashed line is the trajectory of the null shell. In this dotted red line is the trajectory of the future horizon. And note that inside the shell, null shell trajectory, the space-time is flat, and here is the metric that can describe the geometry. And the outside of the shell, by Birkhoff's theorem, the space-time is a short shell. So it is also useful to define the null coordinates that are u and v inside the shell, and us and v outside the shell. We define them in such a way that v is continuous as we cross the shell, and us is not. So by matching the geometry at the trajectory of the null shell, we have this relation between u and us. So the type of the field that we are using is a massless, minimally coupled scalar field that in a general space-time satisfies this wave equation. And in a null shell space-time, the field can be expanded in terms of a complete set of modes, F and F star, and A dagger are annihilation and creation operators, where modes F satisfy the wave equation and has this general form in terms of an angular part and radial and time-dependent part. So inside it is the product of the radial part and the time-dependent part. I'm going to use this in the next slides. So considering this general form for the F that satisfies the wave equation and the geometry of the space-time, both inside the shell and outside of it, we can find this wave equation will reduce to a differential equation for the radial part of the modes. So that in the next slide, I will talk about the solution to this, the mode equation inside the shell that are fairly simple. So the solution to the mode equation inside the shell, to the mode equation for the radial part of the mode, has this form in terms of spherical Bessel functions. And CL here is a normalization constant that can be found by imposing the boundary condition on the past null infinity. We define the in vacuum state such a way it has this form on the past null infinity. So imposing this condition, CL can be determined. But instead of solving that more complicated differential equation for the radial part of the in modes outside the shell, we take a different approach. So we map the problem of finding the in modes outside the null shell and the future horizon that I showed here with this green square, with finding them finding the in modes in this green square that is in the pure Schwarzschild space-time. But why can we do that? Because just suppose that if we take this Cauchy surface in the null shell space-time, that is a union of the null shell trajectory and a part of the past null infinity, and map it here in the pure Schwarzschild space-time, and considering the initial data on the Cauchy surface, we get the same evolution for the in modes, because the geometry in this green square and this green rectangle are same. They are described by Schwarzschild space-time. So, but here, if we map this Cauchy surface on to this pure Schwarzschild space-time, the union of the V equals to V naught and the part of this past null infinity doesn't form a Cauchy surface. And that's why we added this piece that is a part of the future horizon. And to find the in modes inside this green region, we need to specify an initial data on the future horizon. And we do that by using the fact that the in modes are continuous at this point, that is where future horizon and the null shell surface meet. So now we have a different problem, and that is finding the in modes in the pure Schwarzschild space-time outside the null shell and H+. So we expand our in modes in terms of a complete orthonormal set of modes, FH+ and FScry+. FH+ are positive frequency on the future horizon, and they vanish on the future null infinity. And FScry+ are those modes that are positive frequency on the future null infinity and are zero on the future horizon. So here we expanded the in modes in terms of a FH+ mode and FScry+ modes. Here, A and B's are the matching coefficients that can be found by the usual scalar product on the Cauchy surface on the null shell in the pure Schwarzschild space-time. So here are our partial analytic results for the matching coefficients that can be used to construct the in modes everywhere outside the future horizon and the null shell. So we have represented them in terms of scattering coefficients and the in modes on the Cauchy surface. So to see that if this method works in constructing the in modes, we tried to construct the in modes in the region where we can test our results. So we did this on the future horizon for S wave, L equals 0, and where SCRI plus modes vanish, and the psi n that I introduced before can be expanded in terms of H plus modes. And the initial data that we put on the part of the future horizon that is a part of the Cauchy surface in the Schwarzschild space-time. I'm going back to the slide and show you. So we need to find the scalar product on this region. So the initial data that we put here has for S wave has a simple form of it's same as a two-dimensional case, and it has a V dependent part and U dependent part, and the V dependent part is that goes like e to the minus I omega V, and we constructed the V dependent part of the in modes to compare our results. So here is the real part of the in modes, and the left hand and the right hand one is the imaginary part of the in modes, and where they goes to the form of they value at the null shell are like the initial data that we put on the future horizon. So and I will show this explicitly in the next slide. So this solid curve is our numerical result for the in modes outside the null shell, and this dashed line is the exact result in or our initial data we put on the future horizon for V less than V naught. So, and we can see that here is the I plotted for an interval between V naught to larger V, and at V equals to V naught is we can see that the mode function is continuous. And here is the same for the imaginary part of the in modes. Okay, as another example, we did this computation, the construction of the in modes on the future horizon for larger frequency. So for omega equals to 9, we can see that we expected that there's no scattering in this case, and the case, the 4D case, is more like a 2D case. And here I have shown the in modes in 4 dimension with blue dashed line. I hope you can see that. And the solid yellow curve is the 2D in modes. You can see that they are in agreement, and this shows that our method of constructing the in modes are working well. So the reason that for larger frequency we expect that the in modes has a form like two-dimensional case is that in the mode equation, when omega, the frequency is large, we can ignore the effective potential and there is no scattering. So here is the real part of in mode, and I did the same for the imaginary part. For the renormalization, what we did is we subtracted the unrenormalized expectation value of the stress tensor in unruh state from the unrenormalized expectation value of the stress energy tensor in vacuum state. And because this difference is, it just depends on the state of the quantum field, we can say that the difference between the renormalized counter, it's same as the difference between the renormalized counter terms. So the advantage of this method, the subtraction method here, is that we can just compute this quantity, this difference, the difference between the unrenormalized terms, and add them to the expectation value of the stress energy tensor in unruh state that is renormalized. And this has been computed by Levy and Ori before. Then what we need is just finding this difference that is related to the 2-point, to the derivatives of the 2-point functions that are that I have written here in terms of in modes. So the second test that we did to test our method is the computation of the stress energy tensor in 2D, where we have a perfectly reflecting mirror at the origin. And in this case, there is no scattering, and that complete orthonormal set of that we are using, psi h plus and psi scribe plus has this simple form. We expanded the in modes in terms of the FH plus modes and scribe plus modes, and found this analytic expressions for the matching coefficients. And we use them to construct the 2-point functions, and also found use those 2-point functions to find the expectation, the renormalized expectation value of the stress tensor in vacuum state and unruh state. So here is our result. The vertical axis is the TT component of the delta T, and delta T means the difference between expectation values in unruh state and in vacuum state as a null coordinate US. The solid dots are our numerical results, and the curve is this solid curve is the known results. So we can see that there is a good agreement between our results and the known results. This has the known result has been computed by people before, both the renormalized renormalized expectation value of the stress energy tensor in vacuum state and in unruh states. So in a summary, we developed a method that can be used to compute the expectation value of the stress energy tensor in a 4-dimensional short-shaped black hole space-time that forms from the collapse of a null shell. And we showed that this method works in 2D case. And also we have partially constructed the in modes everywhere outside the null shell and the future horizon And at the end, we are working, this work is in progress, and we are trying to find, to use our results for the in-modes to compute the stress energy tensor. Thank you.
Okay, thank you very much. A very detailed talk. We have some time for questions. So please go ahead, switch on your microphones and ask the questions.
Sorry, I stopped sharing my contents.
That's okay. Okay, very good.
Okay.
Mhm. So any questions? I have a technical question regarding the four-dimensional case.
Okay.
Do you think this is just a technical problem that you are doing now? I mean, from the conceptual point of view, it's exactly the same, the case you have analyzed now and the four-dimensional case. Are there any conceptual differences, or do you expect exactly the same thing?
I mean, the form of you mean the form of the stress energy tensor for the late times, you mean that is in agreement with the exact results, and what we are going to find is the same as the 2D case?
Yeah, exactly.
That can be possible. I don't know, because we are not done with the computation of the stress tensor, but we expect that goes to the expectation value of the stress energy tensor in unruh states at late times.
Okay. Okay, thank you. Thank you, sorry. Okay, if there are no more questions, then we continue with our next speaker, who is Paul Anderson. Paul is going to talk about the linear growth of the two-point function for the unruh state in 1 + y dimensional black holes. So, Paul, please go ahead.
Okay, can you hear me?
Yes.
All right.
Very good.
Okay, yeah, I would like to talk about a result that was certainly for me rather unexpected regarding the unruh state in 1 + 1 dimensional black holes. This work is with an undergraduate at Wake Forest, Zachary Schofield, and with Jenny Trashen at the University of Massachusetts in Amherst. So, as everybody in this session is very familiar, Hawking predicted the black holes that form from collapse evaporate, and you get a thermal distribution of particles at late times. Unruh found a state that applies to eternal black holes. You don't have particle production in eternal black holes. You have the region outside the horizon is static. But what he found was a state which gives you a flux of particles at infinity, which at late times for a black hole, which gives you the same result at late times as you get for a black hole that forms from collapse and evaporates. It's a significantly easier mathematically to work with eternal black holes. And so the unruh state's been used to study quantum effects in black hole spacetimes. Another simplification that's used extensively is that in 2 dimensions, it's extraordinarily much easier to work with, particularly with massless minimally coupled fields, which are conformally invariant in 2-dimensional spacetimes. An enormous amount of work has been done on quantum effects in various 2-dimensional spacetimes and in various theories of gravity, such as dilaton theories and such. The 2D simplification I will use throughout the entire talk. Working with eternal black holes we'll do first, but that will get relaxed. To investigate quantum effects, what we decided to do was to look at the symmetric two-point function, the Hadamard function, for the usual scalar field in 2 dimensions, massless, minimally coupled. And we're going to look at that in various two-dimensional spacetimes with horizons. And I'm going to begin the talk with eternal black holes and the Unruh state. And I'm going to focus on the Schwarzschild de Sitter spacetime. For one thing, that's a little bit less familiar for some people. And so it's kind of an interesting spacetime. It's got 2 horizons, and that actually comes into our result. So it's nice to sort of focus on that and then to talk about what happens in other cases. We'll discuss I'll then discuss the computation of the two-point function for a massive field. That's the part that I'm working on with Zach Schofield for Schwarzschild de Sitter in 2 dimensions. So we'll look at the massive field, which is a little different. There's no conformal invariance in that field theory. And finally, I'll consider a Schwarzschild black hole that forms from a collapsing null shell, the thing that Chauret was just talking about, except that I'll consider the problem in 2 dimensions. So Schwarzschild de Sitter has Penrose diagram, which sort of goes on forever. But the part that we'll be concerned with is the part, the diamond here, which is in purple, region 1. That's the so-called static patch. That's where the geometry looks similar to the Schwarzschild geometry. The metric function f starts out like the Schwarzschild function, but has a piece that's related to the cosmological constant as well. That's really where we'll focus in this talk. There's the interior region of the black hole, the exterior cosmological region, which is asymptotically de Sitter. Key points are going to be the horizons. There's a past cosmological horizon, a past black hole horizon, a future cosmological horizon, and a future black hole horizon. The wavy lines indicate the black hole singularity. So what happens in Schwarzschild de Sitter is actually the radii of these 2 horizons are related to each other in the following way. And the result is you have a maximum size for the black hole. And when the 2 horizons come together, and the maximum size for that black hole has 0 surface gravity. That's not the case I'm interested in here. We won't talk about that, but that's just sort of the extreme. So we'll talk about the case where the 2 horizons are separated, as in this Penrose diagram. Now, again, as in other spherically symmetric or 2-dimensional analogs of spherically symmetric spacetimes, it's used to work in radial null coordinates. These are the right moving coordinate and the left moving coordinate, where our star is the usual tortoise coordinate. We also have Kruskal coordinates and Kruskal coordinates now for 2 horizons. So you can have a Kruskal coordinate associated with the black hole horizon, and you have Kruskal coordinates associated with the cosmological horizon. The ones for the black hole are defined in exactly the same way as Schwarzschild spacetime, and these are the obvious analog, okay, for the cosmological spacetime. Now, there's a well-behaved time coordinate on both of these future horizons, which Gregory, Castor, and Trashin found. And there's more detail than I want to go into here about this, but this is the metric in terms of that coordinate, capital T, and the radial coordinate R. And the key point is down here that on the future black hole horizon, the V coordinate, the left moving coordinate, which is regular on that horizon, is equal to capital T. And on the future cosmological horizon, the right moving radial coordinate U, which is a regular coordinate on this future cosmological horizon, is equal to the time coordinate capital T. So we'll be using that. So we look at a massless minimally coupled scalar field, and we want to define the Unruh state. This was actually defined by Tadaki and Tagaji first, and then by Markovic and Unruh. And the idea is that we look at solutions to the mode equation that are positive frequency with respect to the Kruskal coordinate time for the black hole Kruskal coordinates on the past black hole horizon. And we take, that's one set of modes. We take another set of modes, which are positive frequency with respect to the crustal coordinate for the cosmological horizon on that past cosmological horizon. Together, they form a complete set of modes. Each mode is actually this set, the black hole ones are 0 on the cosmological, and the cosmological are 0 on the black hole horizon as well. So these form a complete set of modes together. And so we can quantize the field in terms of them. And that's the unroot state in Schwarzschild de Sitter spacetime. So the 2-point function, the symmetric one that we're going to look at, is just given by the expectation value. The u here means simply we're taking that expectation value in the unroot state. And it's the field, and then we just reverse the order of the indices to make it symmetric. Substituting in, we end up getting products of the mode functions that are positive frequency on the black hole horizon and those positive frequency on the past cosmological horizon, plus their complex conjugates. There is no scattering for the, as Shorey mentioned, in 2 dimensions, there is no scattering for the massless minimally coupled field because it's conformally invariant and the space is conformally flat. And as a result, we know the solutions, those solutions that we have here are actually solutions throughout the entire space-time. And so we can then immediately substitute them in, and becomes a very simple integral compute in terms of cosine integral functions. The key point being the cosine integral function is related to Euler, at small values, is related to Euler's constant plus a log term plus terms that vanish as that argument goes to 0. Omega 0 here is an infrared cutoff. You'll notice that this is infrared divergent. And that's very typical for the 2-point function for a massless scalar field in 2 dimensions. In flat space in the Minkowski vacuum, this 2-point function is infrared divergent. So it's not always true that you have the infrared divergence, but it's very, very common. And typically what one does is simply put in an infrared cutoff. And so that's what we're looking at with this omega 0. All right, so when one does that, then what I want to show you, the specific one I want to show you, because it's easier it's relatively easy to see, is we'll let one point be on the future black hole horizon and the other be on the future cosmological horizon. And let's take the 2 times equal, but the spatial points are obviously separated. If we do that, it turns out that the crustal coordinate u for the black hole horizon is 0 on the future black hole horizon. For the cosmological horizon, the crustal coordinate v is 0 on the future cosmological horizon. And so what we get is that this difference then simplifies to this simple form, which is the key part is goes like e to the minus kappa bt and e to the minus kappa ct for these differences. Then we put that into here, use the log part, and notice that these are exponentials. And so what we end up getting is this interesting form for the 2-point function with this separation that is equal to the sum of the 2 surface gravities times this time coordinate capital T minus a couple of constants. Okay, this is when one point is on the future black hole horizon, the other point's on the future cosmological horizon. We get this linear growth in the 2-point function. Now, I don't have time to go through the calculations, but you find the same linear growth if you take a general separation of the points anywhere in the static fraction, even outside the static patch. Okay, in this case, you have a constant. This is not a constant anymore. This is a function of r and r prime, but there's no function of time. The only function of time is coming here for this 2-point function when the 2 points are equal. The 2 time functions are equal. So this is now then the general result for the 2-point function for this field. It grows linearly in time. Now, once we found that, and I will say Jenny Trashan's the one who found that, we went to look at other cases for the massless minimally coupled field and found very quickly in Schwarzschild spacetime for the unroot state that you get exactly the same kind of thing. Of course, there's only one black hole horizon there. There's only one horizon there, so there's only one surface gravity, but it goes like the 2-point function goes like the kappa times that time coordinate. There's a time coordinate which you immediately get by just reducing the space-time down to Schwarzschild, setting the cosmological constant to 0. You can also look at de Sitter space. If you take de Sitter space set the mass of the black hole to 0 from the Schwarzschild de Sitter, you end up, this Unruh state ends up reducing to the Bunch-Davies state in de Sitter space. This is in 2 dimensions again. And we found the same divergence, which is not surprising there because there's a known divergence in 4D for the same thing in de Sitter space for the Bunch-Davies state in the massless minimally coupled scalar field. There's a class of Bose-Einstein condensate analog black holes, spacetimes, which have been developed to look for experiments. People look at something called the density correlation function, and one can look at the Unruh state in those spacetimes as well. And it turns out that in those cases, there is this linear growth in the Unruh state. And also, Jenny Trashin came up with a general argument that we should have, which I won't go into here for time issues again, but there's a general argument that linear growth should occur whenever there's a past horizon and whenever there's no scatter. So we expect that if we looked at Reisner-Nordstrom in 2 dimensions and things like that, we would continue to get this behavior. So the question though is, what do these situations have in common? Okay. Well, one thing I should have put there, I just realized now, is they're all in 2 dimensions. And as I said, I'll stick to 2 dimensions for this talk. The second is we have a space-time with a static patch and at least one past horizon. Okay, and again, the general argument says that then we should have this growth. We've looked at a massless minimally coupled scalar field, and we have an infrared divergence in the 2-point function for the field. Okay, so those are some things that are in common. So we could ask, well, what happens if we relax these? And so the 2-point function, the first thing, this is actually the second thing we did to relax it, but it's related to directly to Schwarzschild de Sitter, so I decided to talk about it first. This is the work I'm doing with Zach Schofield. So the 2-point function in 2D flat space for the massive field is infrared finite. So we decided we'd add a mass term, look at the massive field in 2D. Now in Minkowski space, there is no infrared divergence for this field for the 2-point function. However, in Schwarzschild de Sitter spacetime, the equation for the mode functions, when you have a mass term, has an m² f, where f is this metric function again, this GTT function, and it multiplies the mass, and so you get basically an effective potential. Okay, and so what's different, what's interesting though, and what's different from Minkowski space is that this effective potential is 0. This function vanishes on both the cosmological and black hole horizons. And so the conditions for the Unruh state for this massive field are exactly the same as the conditions for the massless field, since the field's effectively massless on the horizons. And we define the Unruh state by positive with frequency with respect to the appropriate Kruskal coordinate on the past horizons. So it's actually not clear a priori, at least not to me, if there would be an infrared divergence or not. I suspected not, but it wasn't clear. The other thing that's different is that the field is not conformally invariant. The space is still conformally invariant. All 2D spaces are conformally flat, but conformally flat rather. But the effective potential results in scattering. And so now we have scattering. So the mode functions are much more difficult to compute. They don't have a nice analytic expression for them everywhere. Well, it turns out in that case, it's much easier to expand the Unruh modes in terms of modes for the Bulwer state. The Bulwer state is sort of the natural vacuum state in Schwarzschild spacetime. You can generalize it to Schwarzschild de Sitter in a clear way. I don't have really the time to do this, but essentially what you do is you take positive frequency modes with respect to the usual time, not the Kruskal time, on the past horizon. I'm only illustrating this for the black hole horizon here due to lack of time, but the exact same thing goes for the cosmological horizon. If we want to look at the modes that are the Kruskal mode, the modes for the Unruh state on the cosmological horizon, we can expand those in terms of these modes as well for the of similar modes as well for the Bulwer state. And then one can compute these Boole-Wark modes numerically. We've done that, or Zach has done that, and we find that actually what happens is that scattering effects remove the infrared divergence in the Boole-Wark mode. You can see right now, right here, that if you let omega prime go to 0, that this would go to infinity. So the mode itself is divergent. I haven't shown you the Bogolubov coefficients, but if I did, you would see that this is also infrared divergent here if you just plug this into it. So it is for the massless case. But in the massive case, it turns out that this is finite, and this is also, this integrand is also finite. Now, this is just for the modes for the unroot state. So we don't know for sure that there are no infrared divergences in the 2-point function, but it seems quite likely that the lack of infrared divergences here and here mean there are probably no infrared divergence in the 2-point function. And right now that this work has begun, is sort of, in process. And so this is as far as we've got. The next step is to compute. We're in the process of computing these modes, and then we'll use them to actually compute the 2-point function and find out whether it grows linearly. This last example that I want to give is for the collapsing null shell spacetime that was talked about by Chouret in the previous talk. This time it's in 2 dimensions. It's the same Penrose diagram. If we put a mirror in this, we put a mirror here, a perfectly reflecting mirror, so the scalar field vanishes there, then we get exactly the same Penrose diagram as we get in the 4-dimensional case. Again, to remind you, the dashed line, the blue dashed line is the trajectory of the shell. The red dotted line is the future horizon, the event horizon that forms from the collapse of the shell. And this BH is sort of the value of the coordinate V for the last null ray the null ray that actually forms the horizon. Okay, so we find null short coordinates. She went through this, so I'll just remind you quickly. We have null coordinates inside the shell, goes like t minus r and t plus r as usual. Outside, the usual Schwarzschild null coordinates t minus r star and t plus r star. The space-time outside the shell is inside is flat, outside is Schwarzschild. And this is the matching between the coordinates. The v coordinate is continuous across the shell. The u coordinate is not. It has that behavior. Okay, so the modes for the in vacuum state, the state has to vanish at r equals 0. So as well as this mode, which gives us positive frequency at past null infinity, we need this one to get vanishing at r equals 0. So this is the solution to the mode equation in 2 dimensions for the in vacuum state. Now there's no scattering. Again, we're back to the massless minimally coupled field in 2 dimensions. So the only difference between inside and outside the shell is that outside the shell, the u coordinate goes to that function up here of us. And oh, by the way, w, capital W is called the product log function. Okay, that's the product log function. So u as a function is thought of then as a function of the right moving null coordinate in Schwarzschild spacetime. If for this solution, if we're in the if we're outside the null shell. Now, one thing to notice that actually I didn't even really think about till fairly recently is that this mode function is infrared finite. We set omega to 0. The mode function goes to 0. And so this implies there's no infrared divergence for this state of the 2-point function. So we can have a 2-point function for the massless minimally coupled field in 2 dimensions, which has no infrared divergence if we choose the right state. And that's exactly what we have here. So there's no infrared divergence. Again, it's easily computed analytically because of this simple form. And what one finds is this product here. And I don't have time to go through all of the details, but essentially what happens is, maybe I can just run back here. If you look here, it turns out with this product log function, it turns out when us goes to plus infinity, then the coordinate u goes to vh. Okay, so u goes to vh when us goes to plus infinity. That's the main thing I wanted to show here. And so this at late times, this V minus U goes to V minus VH, the V prime minus U goes to V prime minus VH. And then this one is more complicated. When you work it out, which is not difficult, but when you work it out at late times, at early times, you don't have anything like this. I mean, you have this, but you don't have anything like this. But at late times, what you find is the same kind of growth, linear growth in the coordinate t as you have for Schwarzschild, for static Schwarzschild spacetime in the Unruh state. In that sense, it approaches the Unruh value. But you also have, interestingly and unexpectedly, again, the log term. So there's actually some growth, subleading growth due to this log term. And then you have a term here which just depends on R. Okay. So we've investigated then the 2-point function for a massless many coupled field in the Unruh state in 2D spacetimes with horizons. We find if we have the two horizons in Schwarzschild de Sitter, we get linear growth, which depends on the sum of the surface gravities of those two horizons multiplied by the time. Okay. If there's just one horizon, it's just the surface gravity of that one horizon multiplied by time coordinates that's good on that single horizon. In 2 dimensions, this seems to always be the case. But we relaxed this when we found similar late time growth when we have a null shell that collapses. So this is, I think, important. This implies the growth does not depend on the existence of a past horizon, because there is none. It almost certainly depends on the existence of a future horizon, but not a past horizon. And it does not depend on the existence of an infrared divergence of the 2-point function. So it's independent of both of those. Okay. The argument we had, general argument we had, didn't really depend on the infrared divergence either, but it did depend on the past horizon. Although there's good reason, if one looks at Hawking's calculation, to see that that this is perfectly consistent with that argument. It's just that it goes beyond that argument. And we begun investigating a massive field in 2-dimensional Schwarzschild de Sitter. And again, preliminary evidence indicates there may be no infrared divergence in this case. In the 2-point function, we simply don't know about the linear growth at this point. Thank you very much.
Okay, thank you, Paul. It was a very detailed talk. So we have time for questions, very short questions. First, let me ask, Carlo, are you there? Carlo Rovelli. Well, he's still not there. Remember, he was having an operation today, very small operation. Let's hope everything will be fine. Okay, some questions for Paul. Paul, let me ask you a question regarding the two definitions or two concepts of surface gravity you use. You have the usual one, you have also a cosmological surface gravity. So in fact, you have two different temperatures. What's the difference, the physical difference between the two of them?
Okay, yeah, so that's exactly right. We have two different temperatures. There's a higher temperature related to the black hole horizon, and there's a lower temperature related to the cosmological horizon. So you get two different fluxes of radiation. Okay, I didn't talk about this aspect of it, but so what you get is you get a flux of radiation that is right moving towards the future cosmological horizon at the black hole temperature, and then you have a flux of radiation at the lower cosmological temperature, which is left moving and goes through the black hole event horizon and into the black hole. Okay, and it turns out that if you look at, for example, the stress energy tensor in this case, that it's perfectly finite everywhere, including everywhere on the future horizons and in between. It diverges as it does in Schwarzschild spacetime on the past black hole horizon, and also diverges on the past cosmological horizon. But one doesn't worry about that for the Unruh state, because those horizons don't exist for the more realistic case of a black hole collapse. So this confused people initially because you can't get this. There's some way, which I won't go into, which I don't really understand, to get some kind of a temperature, single temperature in Schwarzschild de-Sitter. But basically, you can't get a single temperature if you put the horizons at the same temperature. You put the field on the horizons at the same temperature, then you'll get a divergence on one of the future horizons. But this way, you don't get a divergence on either future horizon. You just have these two fluxes at different temperatures.
Okay, thank you. Charles, you have a question?
Yes, hello. It was kind of just answered actually. My question was related to whether your work has any bearing on whether there is like an equilibrium temperature in Schwarzschild de Sitter spacetime. So you've kind of already touched on that already. But I could ask, what is your, in your opinion, even if this work maybe doesn't have a bearing, in your opinion, do you think there is an equilibrium temperature? Do you think that makes any conceptual sense, or do you have to have two different temperatures associated, one to each horizon?
There has been work, I apologize to the authors of the work, I've forgotten the authors, but there is a paper out there, at least one, where the authors claim to define, in a certain sense, a single equilibrium temperature for the Schwarzschild de Sitter black hole. Yeah, I'm sorry, I just don't remember the authors, but that has been done. It works a little differently than the usual sense. The Unruh state works in the sort of traditional sense. That temperature works a little bit differently, but there is some way to define a single equilibrium temperature in Schwarzschild. Yes.
Okay, thank you.
Okay, thank you, Paul. Any other question? So we were supposed now to start with, Carlo, you are there. I was waiting for you. Okay, very good. So then we start with the last talk today by Carlo Rovelli, which is about why the black hole information problem is a false problem. So thank you, Carlo, go ahead.
Thank you very much. Just let me share screen. Portion of screen. Okay. Good. If there's any problem, you let me know. I assume that
everything is fine.
You see. Thank you. So sorry, just setting everything. This is the title, why black hole information problem is a false problem. And what I'm going to present is work in some papers of mine, but also a rather shared point of view by a community working in mostly loop quantum gravity, but also in other approaches to quantum gravity. So some of these ideas are well known by some part of the community, and it's quite a remarkable situation that research community is split with very different prejudices regarding the black hole information problem. So I'm going to argue that there is some confusion. There are at least 4 elements of confusion that pile up. They're all related to one another. The first is between event horizon and trapping horizon and the consequences of that, and the role of quantum gravity in that. The second is between thermodynamical entropy and von Neumann entropy, which is related to the first. The third is between bulk states and boundary states of a black hole. And finally, the culpable, which depend from the others, is between different versions of holography and their consequences. And the thesis I'm going to defend is that unitary evolution and equivalent principle, in the sense sort of quantum mechanics that at infinity conserves information, and generativity with quantum field theory, local quantum field theory, standard local quantum field theory, being valid in all finite regions of space-time, including across the horizon, inside the horizon, outside the horizon, are compatible, contrary to what it's often presented. and claiming that there is some incompatibility and therefore a problem with an information puzzle about black holes. So I will point out exactly what is the physical problem, the physical hypothesis in theorems, like for instance the firewall theorem, meaning it's a possible hypothesis, but it's just an arbitrary hypothesis, it may be right or wrong. And then I will give an example, just a proof of principles that there is a unitary quantum black hole, which in fact is an example which has been studied and has astrophysical implications. Let me start by saying that what I'm talking about, it's black holes, namely sort of the things within the sky as far as we understand them. By this, what I mean, how much time do I have? Is that?
You have 35 minutes.
Oh, wonderful.
We can have some more time.
Yes, thank you. I'll try to reserve that for discussions. This is I know is a discussed topic, it's a disputed topic. So the reason I'm saying that is because sometimes one starts from a mathematical definition of black holes, like a black hole is an event horizon, and this compromises the entire consequence, as you will see in a moment. Now, all the phenomenology that we see in the sky is well accounted for by general relativity, by classical general relativity. In fact, for the purpose of this talk, I disregard rotation. So I'm thinking that to some extent, to a first approximation before a number of things, like things falling to the black hole, the outside of the black hole is actually the outside of the collapsing star that formed the black hole, if black hole is formed by a collapsing star, described by a portion of the Kruskal space-time. So this is a relevant portion of the Kruskal space-time. It has a black hole part, the exterior part, and the horizon. And the key point is, of course, that this disregard quantum phenomena. Let me just draw this in a more upside way. So this is the brown thing is the star, this is horizon, this is chi minus, this is chi plus, and we expect quantum phenomena to happen in some region. So we expect this picture, this conformal diagram to be non-physical in some region, which at least includes that what we expect, the region of the curvature become Planckian. Say R, I don't know, Kretschmann invariant, the square root of the square of the Riemann tensor. When if the order of the Planck length to the -2, this is the dimension, we all sort of agree that most likely there is a strong quantum phenomena there. So at least there should be quantum phenomena. Now, key observation is that if we fold in the fact that we expect Hawking radiation to exist, the Hawking radiation sort of outside the horizon, it goes through Sky Plus, and its back reaction is going to shrink the horizon. I'll be slightly precise for the moment. I'll be more precise in a moment. So the horizon becomes smaller and smaller and smaller. If Hawking writes, which is an assumption of everything I'm saying, in a time of the order of the mass cube in natural units, where the mass is the mass of the initial mass of the black hole, mass of a collapsing star, the horizon becomes very small and goes toward a Planck size. Now, outside the horizon, this is a zooming, this region here, which of course is small in the picture, but is huge in reality because it's a conformal diagram. Outside the horizon, the curvature goes as the mass of the radius cube, which near the black hole horizon means the radius to the -2. And so when the radius starts approaching a Planck size, the curvature becomes Planckian outside the horizon. That's a key point. That's a key point. That's a key observation. So according to standard Hawking theorem, we get in a quantum gravity regimes outside the horizon before getting to infinity, which means that we extrapolate classical general relativity, assuming it to hold all the way to infinity. We're making an assumption about quantum gravity, which might be very well be a wrong assumption about quantum gravity. In fact, all the theories of quantum gravity that I know indicate that that's a wrong assumption about quantum gravity. So when people write a a conformal diagram like this one, where there is an assumption that the black hole sort of disappears, and therefore the event horizon continues, because there is a part of space-time which is hidden for Sky Plus. So this is a genuine event horizon. There's a genuine event horizon here. One is making an assumption of what was going here, so quantum gravity assumption. Let me just remind you, I think we're relativists, we know, but just for clarity, an event horizon is the boundary of the past or future infinity. So it's something that depends on what happened in the future. And we know here in the future, we see that it's quantum gravity that comes in. It's not just, you cannot avoid quantum gravity here. A trapping horizon is, for instance, the boundary of the region where the area of the outgoing null surfaces decrease. So in other words, this is an horizon in the sense of a trapping horizon. There are a number of similar definitions, an apparent horizon, a dynamical horizon. So this is an horizon according to any of these definitions, but we don't know whether it is an event horizon or not, unless we assume something about quantum gravity. So it's perfectly possible that the other side of the quantum region is seen from future infinity, and there is no event horizon. So what I'm saying is that it's very possible that there is no event horizon, which is an observation made by many people. Hawking notoriously made these observations a time ago when there were articles saying there are no black holes. Because if you define a black hole in terms of the event horizon, then physically quantum gravity just says that there's no, may very well say that there's no black hole. Now, of course, as long as user observer are in the first part of Sky Plus, assuming that this is an event horizon is a good approximation, but only for a while. Then you might go over it. The second confusion, so the first is between trapping horizon and event horizon. The second confusion is about entropy, what we mean by entropy. And of course, there's a thermodynamical entropy, which in some sense counts the degrees of freedom. This is a formula on Boltzmann grade, which in quantum mechanics, it's roughly given by the dimension of the Hilbert space of the system whose entropy we are considering, the system whose degrees of freedom comes in the interaction that it's the exchange of heat and work that defines thermodynamics. And then there's von Neumann entropy, which measures the entanglement between two systems. So if you have a system A and B in a pure state psi AB, this is the density matrix of just A when you trace over B, and you compute its von Neumann entropy, trace rho log rho. And this tells you sort of how much information is lost into B. Now, of course, in a normal situation, you expect von Neumann entropy to be smaller or bounded by this entropy here, because if the dimension of HB is it's whatever it is, the von Neumann entropy you cannot store more states in HB than the dimension of HB. But, and this is the key point, there are a number of situations in which the notion of which states are accessible, it's ambiguous. And that's a typical situation. Imagine that there is a box that for some time is open, this box B, and at some point you isolate it very well. You construct a wall around it that it's an isolator. So you have no exchange of heat and work, so no exchange of energy between B and a larger box A. And imagine you're outside and you do experiments and you deduce the entropy of A. Now, since B is isolated, the change of number of states in A, which is relevant for your entropy, is just the state of A minus the state of B. So the thermodynamical entropy you interact with is the one of A. But of course, the von Neumann entropy can be larger because you might be entangled with something inside B that does not participate to A, to the number of degrees of freedom of A with which you are interacting. And that's exactly the situation of a black hole, because when you're outside the horizon, you're interacting with the degrees of freedom which are on the horizon or just outside the horizon. Remember that the Hawking radiation, it's actually a phenomenon of the size of the black hole itself. It's not a microscopic phenomenon. right? So it sort of produces the distance of the order of m from the black hole. You're interacting with those degrees of freedom, but nothing prevents the fact that you're entangled with inside degrees of freedom, which means now if you put the two things together, that if the horizon is not an event horizon, like in this case here, the horizon is just a dynamic horizon, trapping horizon, for the time during which the approximation of considering it's an event horizon. So for the time until you are at this point here, the early time of an observer sky plus, that's the thermodynamic entropy. It's only the one given by the boundary degree of freedom and not a bulk degrees of freedom. Of course, it's weight more. That approximation is not good anymore. You don't. You see that there is no event horizon, and you have access to the information which is inside. All right. Now, remember, to help the understanding here, that a black hole, a natural, good, and in fact, nice mathematical properties, which I'm not going into foliation, to think about what's the inside of black hole, is just to take essentially constant R and maybe cut out from the on the horizon. So if you take a point of the horizon and you want to know what the volume inside, and you define the volume like in Minkowski space, like the sort of the maximum spherically symmetric area that a surface can get inside, it's very easy to see that that's a shape inside. So the shape of this blue surface here, it's a long cylinder that, as time goes on, as you get closer to the singularity, becomes narrower and longer. And just to give a sense, for a stellar black hole at the end of the Hawking evaporation, the distance between the horizon and the star, the space-like distance, is 10 to the 75 light years. So black holes they age, and seen from the outside, they are only determined classically by the microscopic parameter, mass, area, angular momentum, but not inside. Inside, they're very different, okay? A black hole of a certain area, which is young, produced by a small star, and a black hole of the same area, which is old, produced by a big star and then evaporate, they're completely different inside, right? So this is what is happening. I mean, the black hole becomes longer and longer and longer. If you come in at some point, you see you are in a you don't cross this small surfaces here, you cross this surfaces there. So the internal structure of a black hole is different at different times. Okay, and a black hole can have a small throat and a large interior. This is essential, I think, to think about black holes. Now, there is a recurring idea, that when the black hole shrinks, and that's the origin of Page argument for the Page curve, the Page time, and then this idea that late Hawking quanta are entangled to early Hawking quanta, which is very common in some part of the community. This argument is based on the idea that when the horizon shrinks, of course, it's not an event horizon. The one that shrinks is it's a trapping horizon, the dynamic horizon. So when the black hole becomes smaller, 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 because it loses, because of the back reaction of the Hawking radiation, this negative energy that goes in. The number of possible states go inside diminish. Now, this is a nonsense from the point of view of quantum field theory, which there's no reason to assume is wrong, and I'll get back to that, because we're not in a quantum gravity region. Quantum gravity region is up there. And you just use the axioms of local quantum field theory, and the algebra of observables on this a surface here, sigma 0, is a subalgebra of the observable on the surface sigma in here. Therefore, the Hilbert space, which is a set of linear functions of the algebra, it cannot be smaller here than there, right? Because there's no, you cannot lose possibility of distinguishing state when going up, because you have more observables, not less. So this, I just sketched the argument more precise in this paper here. Quantum field theory it's perfectly compatible with the fact that the Beacon-Hawking radiation shrinks. It's perfectly compatible that the description of the black hole from the outside in the approximation in which you assume there is an event horizon is given by a number of states, which is bounded by the area. But this does not imply that the description of the black hole obtained, including the observables which are inside, has the same property. There are more states inside which are not seen from the outside, and if not after you get out of the approximation where the black hole is defined by an event horizon. So this is a typical example of this where exactly one can see where this all this comes in. This is the famous Mary Marrolf Polchinski-Sulby paper on the firewall, and they're very clear. The paper is very clear, and there are they derive the firewall on three postulates. Postulate 1 and 2 are essentially unitarity, quantum mechanics, and general relativity, let's say, and postulate 3 is this idea that the dimension of the Hilbert space of the black hole is bounded by the Bekenstein entropy, which is a nonsense if you interpret this as the states inside. All the calculations that give this result, including the string calculation, the loop calculation, all the ones, they're very good, they're very nice, and they're wonderful, but they refer to the black hole as described outside, or to a black hole as defined as having an event horizon, so not even a stationary thing. If the thing is not stationary, and Hawking radiation tell us that it's not stationary, okay, because it shrinks, something happens at the end. You enter in a quantum gravity region, the observer can jump to a new part of Sky Plus where there's more information coming in. Then this postulate is it's just not, it's wrong. It's simply wrong. So the Page argument that the von Neumann entropy must go down because the area goes down just doesn't apply. It's the black hole is not like in Page analogy, like a fire where it cools down to zero and therefore there are no states. It's like a fire in which there's a hole and things fall inside and there is information inside. Good. So this is a perfectly possible picture, which is compatible with all the calculation, including the string theory calculations about the number of states of the black holes, which clarifies that for an observer up to some point, the number of states he can interact with of the black hole, it's bounded by the area, but not later on. Okay, so this is the unphysical assumption in all these theorems here, which implies that so much of later work, which is meant to go around these theorems, it's technically right, but it's physically useless because the problem is not there. Okay, there's some papers which describe this in more detail. So this is the partial conclusion. I still want to give an example of how concretely this happened. Unitary quantum mechanical unity evolution, unitarity and equivalence principle, namely quantum field theory on code space-time being locally valid, are compatible. The apparent confusion comes from confusing event horizon and trapping horizon, so taking the actual physical trapping horizons of the black holes as event horizons, assuming that an approximation is also valid in the quantum gravity regime, which is not, mistakenly because of that, assuming that the von Neumann entropy is bounded by the thermodynamic entropy, which is not in simple non-relativistic physical systems, assuming that there are no internal state of black holes, that all the states are distinguished from the outside before going to the future part of Sky Plus, and confusing, therefore, what is true for a stationary situation from the actual non-stationary situation, which is the true truth of what happened in a black hole because of quantum gravity. So all this leads to the strong version of holographic hypothesis. Of course, black holes have some holographic properties, but not so strong as to say that the number of external state of black holes is bounded by the area. Good. So a very concrete scenario in which this happens, in which the actual quantum gravity transition is computed, has been developed by a large number of people in loop quantum gravity, and it includes sort of three pieces of physics: the star, the bounce of the star itself, the bounce of space-time across the singularity, which transforms, which through a quantum tunneling goes from a trapped region to an untrapped region, and a tunneling of the region outside, which might happen at least when the black hole has shrunk down to Planckian size, if not before, which also can be described by loop quantum gravity. We can compute transition amplitudes from the before to the after. And I'm not going into this calculation. I want just to stress one key point, which is the classical generativity, is a result in classical generativity. I think it's a beautiful result in classical generativity. Namely, if you allow this transition in a compact region, a small compact region here, so it's finite in space, in time and in space, just sort of leaks out of the horizon where it should. All the rest is a classical solution of Einstein equations. So outside is Schwarzschild, inside is a black hole Schwarzschild, and inside here is a white hole. And it seems strange because this is not a this is not a piece of Kruskal, but it is locally isomorphic to Kruskal. So this blue part here, which is entirely classical, is locally isomorphic to this blue part of Kruskal. So you can just take Kruskal, cut and paste, and make this space-time here. And that's of course possible, provided that quantum gravity allows you this transition. There's no reason why it shouldn't provide this transition. Quantum mechanics provide transitions, right? Things go through the wall when you are sufficiently quantum, and here you are sufficiently quantum. So what's next? Well, next is a white hole, and a white hole, it's something that was considered in the past as the name of long-living remnants, which remarkably can be described not with quantum mechanics, to a large extent, there's a quantum feature which I don't want to go into, can be described with classical generativity. So just think of what happened at black hole, time reversed in some sense. You have this long tube that comes back, and it has to be long-living, because this is small. So the energy here is small, but the information is large. And there are theorems that says that with small energy and a lot of information, you need a long time for the information to come out. So you have a teeny thing here, a teeny throat with a huge volume inside, and slowly the volume comes out. Things come out. This is a white hole. Things can come out. They're remnant, and these are being studied in a number of ways, both the quantum transition, and I'm just getting close to the end. There is a lot of phenomenology of these things here, these long-living remnants in the form of white hole, which I just want to listen rapidly. They themselves might be a component of dark matter. I mean, they're a small little thing interacting only gravitationally. What comes out include gamma rays, and they have a role to play perhaps in cosmology. This is not a phenomenology talk, so I'm not going into that. I just put some reference. So I conclude. This is my last slide, which I repeat. Unitarity and equivalence principle are compatible. The idea that because of the Page argument, because of the firewall theorem, because of these kind of things, there is a puzzle to solve about there's something strange that should happen at Page time that save us from the contradiction of our assumptions, comes only because we make wrong assumptions. We assume that this event horizon there is not. We assume that phenomena entropy is bounded by thermodynamic entropy when it's not. We assume that there are no internal states, which is not, and we assume stationarity to describe a phenomenon, which can be unitary precisely because it's non-stationary. And this leads to the misleading assumption of the strong holographic hypothesis that the black hole has no internal state besides its states counted by the Bekenstein-Hawking entropy. So I concluded giving you a scenario, this black to white transition, which is a scenario which I find very compelling, but I don't want to present it here as a necessarily convincing one, just a proof of concept that it's perfectly possible to have a unitary evolution compatible with everything we know, with generativity, with quantum field theory, with quantum gravity just come in where it should, and there is no black hole information puzzle. What comes in, what goes in, the information that goes in come out. And I will stop here. Thank you.
Okay, thank you, Carlo, for this very interesting talk. We have time for questions, so please raise your hands and ask the question. So Swastik, please.
Thank you, Professor Oveli, for a wonderful and very interesting talk. I have two questions. The first is more like a clarification. So you mentioned that about the quantum field theory algebra inside the black hole. Now in semi-classical theory, I mean, if the black hole has some singularity, especially space-like singularity, there is some problem in formulating the quantum field theory states inside. So would it be corrected by a quantum gravity? I mean, would it be taken care of by a quantum gravity correction? And the second question is, this tunneling from black hole to white hole, I mean, is it a necessary consequence of your earlier argument, or it is something which is a likely possibility you mentioned?
Thank you. So the first, I'm getting a bad return.
Swastik, please, your microphone. Switch off your microphone. Swastik. Okay, go ahead, Carlo.
Thank you. The quantum gravity comes in where we expect it to come in. So in this region here. So before quantum gravity come in, I see no reason to doubt that standard quantum field theory on curved spacetime should hold. And quantum field theory on curved spacetime is local and can be thought in terms, for instance, in using the language of algebraic quantum field theory. You don't need to do it globally. Of course, when there is quantum gravity here, I don't expect quantum field theory on curved spacetime to hold anymore. We are in some other, we are outside the approximation where it holds. But the entire argument about quantum field theory is before the quantum gravity region. So it's like, you know, there's no reason to expect that outside the black hole, quantum field theory does not work, but there's the same reason, there's no reason to expect inside the black hole does not work. And behind that, a lot of people have the wrong intuition of black hole, because a lot of people think that the singularity is sort of the center of space-like surfaces. There's always a singularity that stays there. But the singularity of black hole, this is just because the Schwarzschild coordinates are funny. The right coordinates are sort of these ones. I mean, the right space-time structure, this one, namely the singularity is in the future. It's not next to you, it's in your future. So until you get there, I see no reason for quantum field theory to fail. That was your first question. The second question, it's a very extremely good question. Namely, you're saying, I presented a scenario here where I actually talk about the quantum gravity region. I say, look, there could be a tunneling from a black hole to a white hole. And your question is that the only thing that can happen? My answer is that I don't know, partially because we do have a quantum theory of gravity which we can use, which is loop quantum gravity, but I'm not capable of doing global calculations and say what happens. I mean, something else that could happen is a creation of a little baby universe, for instance, or really a disappearance of information inside. But I find these alternatives intuitively much less compelling. It seems to me that there is a simple, compelling possibility. We can compute amplitude of this transition. It doesn't raise anything particularly exotic or exoteric. This is so my answer to you is no, I'm not sure this is the only thing that could happen. But you know, as a scientist working on intuition, that seems to me so easily possible that I would be surprised if nature needs something else for solving the problem.
Thank you.
Okay, thank you, Carlo. Any other questions? I believe Daniele, do you want to ask questions? Your microphone is on. No, probably no questions. So, any other comments, suggestions? Okay, Carlo, let me ask you a quite general question.
Yep.
So if this black hole information paradox is not a problem anymore, so many approaches to quantum gravity are trying to solve exactly this problem. So what do you expect now, how people should try to attack the problem of quantum gravity by considering your proposal that this is not really a problem?
I don't think that the problem of quantum gravity is just to solve these problems. I mean, there are many approaches to quantum gravity. I know several. I know loop quantum gravity, I know string theory, asymptotic safety, a few others. I don't think there are very many, because many are there are quantum gravity ideas, but very sort of partial, incomplete, tentative. The actual number of approaches to quantum gravity where there is a theory just less than the fingers of a hand. And I think the problem of quantum gravity is to understand what happened in black holes, but also to understand what happened in early cosmology and other things. I don't want to go too much in it. And the problem is to show that there's a consistent and coherent theory. And for each one of them to study a possible consequence that we can see in observations. So I was very fast at the end of my talk, but the scenario described by the black to white hole transition leads to some phenomenology, which of course it has not been verified yet. Otherwise, I would have talked about that. But that's a hope. That's somehow we connect a model to reality. I think theoretical physics is not about abstract problems. It's about putting up a theory, seeing that the theory works, and checking with observations. The correct formulation, I think, is not. Let me try to answer more sharply. Is not all the black hole information problem. The correct information is what happened at the end of the evaporation, of the Hawking evaporation. Hawking evaporation is very plausible. We're sort of all convinced that, never been measured, but we're all convinced that it's most plausibly there. So the black hole becomes very small. And then what? Now you need a quantum gravity theory to tell you what happened. So this has been addressed in loop quantum gravity. I would be very happy if instead of talking the sex of angels, making assumptions and then get confused about your own assumptions, people could use other approaches to compute for real what happened at the end of the evaporation.
Okay, thank you very much. Any other questions, comments? If no, so
maybe.
Oh, David, sorry.
Can I have one more question? So Carlo, I've seen your talk already twice, and I still don't understand why you claim that the thermodynamic entropy is not always bigger than the von Neumann entropy. Can you please return back to that argument and see to explain to me what I'm missing there?
Okay.
That's really crucial to recovering the page curve and stuff like that.
Yes. In fact, that's a central. If you want, it's a central point. Sorry, maybe I went a little bit too fast. Think of a concrete thing. So non-relativistic quantum mechanics in a laboratory, a an actual system. And think you have a box A, and inside the box is another box B. And then you get, suppose you have you get entangled with something in B. Okay, so now there is some von Neumann entropy that you obtain when you trace over the box. But now suppose that at some time, B is completely isolated from the rest of the box. So it cannot exchange energy with it. It cannot exchange heat. It cannot exchange work. It cannot exchange information. Okay, it's closed. This is, you can do that in condensed matter. And now you are outside, and you still can exchange energy with the rest of the box. So you have you can measure the temperature, you can measure the energy, and measuring energy and temperature, you can determine the entropy. So you have an entropy. Now, can we theoretically compute this entropy? Of course, is the number of states in A, not the number of states in B, because B doesn't participate if in A there is a single molecule, I mean, when you put a little bit of energy, it's boom, it runs a lot. If there are many molecules, the average is much lower, so the temperature is lower. So therefore, you can have a high von Neumann entropy and a low thermodynamical entropy. Does this make sense, David, to you?
So you're basically hiding a bag of gold there. Is that true, or? Yeah,
exactly. And once you realize that this can be the case, let me add one little thing. Suppose this goes for some time, and then after some time you break this wall, and then suddenly the information comes out, obviously. So I want to say that this is exactly the black hole situation, namely, if you are on Sky Plus for a while, so if you're a distance for a black hole, for a while you have no access for what is inside the hole. So you can be entangled with it without it contributing to the degrees of freedom you can interact with, which are on the boundary. Later on, you break the box because quantum gravity breaks the box, so to say, and you recover the information. Up to there, you can have a very high von Neumann entropy and a low thermodynamic. And specifically, how high, how low? There's an initial mass. So if you think that the outside black hole radiation is purified by the von Neumann, by the entanglement with the inside, you have a von Neumann entropy. You need a von Neumann entropy, which is of the order of the initial mass of black hole. But the black hole shrinks slowly, so the entropy goes down. So the entropy you interact with goes down because now it's a small black hole with a higher temperature in a smaller area. So Page would say, oh my God, I don't have any more states available because the von Neumann entropy is bounded by the Becker say, okay, that's not true.
Okay, thanks.
Okay, thank you, Carlo.
Thank you for asking this clarification, because if you want, this is the core of the talk, so this real argument.
Yeah, precisely, yeah, I agree, thanks.
Thank you.
Okay, Charles, you have a question?
Yes, yes, I'm not sure how well defined my question is, but so it seems like, as you said, the core concepts involved are entropy, and so the difference between thermodynamic and von Neumann entropies. I was wondering how this work, or how these things that you've said relate to other types of horizon, like cosmological horizons. So like other types of horizons that appear in general relativity, like a cosmological de Sitter horizon. And whether entropy associated to these cosmological horizons needs to be also kind of rethought or thought of in a different way.
Yeah, it's a very good question. Obviously, it's an extremely good question, and I'm not sure I have a good answer because I've entirely focused on this point here. It might be person who knows how to answer that. I would tend to say, but without certainty, that it's the same thing for all the other entropies. They're all thermodynamical entropies in some sense. Again, there could be a situation in which the von Neumann entropy can be less or can be zero von Neumann entropy or equal. But to assume that it's bounded by the thermodynamic entropy seems to me a general error, because to the extent in which an horizon is something which is not accessible, hides something which is not accessible to us, we are in the situation of the box. We are hiding something. So I tend to see all the sort of gravitational entropies as boundary properties of the boundary.
Mm-hmm.
And which is reasonable, right? It's proportional to the area. It's something extensive in the boundary. It's there are different ways. There are many ways of viewing that entropy, but it's a way of computing something near the boundary or across the boundary. What happened inside, whatever the far the other side of the boundary, has no reason to be determined by the boundary itself. Once again, holography is a great idea, but you should not over push it. There are situations in which from the outside, there are just things you don't see inside, not because of holography, because they're hidden.
Okay, yeah, I see. Okay, thank you.
Thank you, Carlo. Manu, you have a question?
Yes, my question was related to, one of the important points you mentioned was that the situation is no longer stationary when we are close to the horizon. And that is mainly because we know that Hawking radiation, the back reaction will cause the horizon to shrink. So what other kinds, when it is non-stationary, is it just the horizon shrinking, or do you expect the back reaction to have some other non-stationary effects? Maybe, what I mean is that will the metric change in some way? If it is a Schwarzschild metric, can it cause the back reaction change the metric itself? I mean,
yeah.
Or is it just the,
Yeah, yeah, no, definitely. It changes the metric itself. And we have worked a lot on that. And it's very complicated because, I mean, you know, and we have heard, I mean, to compute the stress energy tensor, I mean, the only thing we can do is to go sort of perturbatively. I mean, you start from the background metric, and you compute the Hawking radiation, and then you compute its stress energy tensor, and then you try to correct the metric, sort of hoping that in some sense will converge. But first of all, even the first step of this calculation is not easy, right? Because we don't know the stress energy tensor of the Hawking radiation. There is a calculation in 2 dimensions, which is very credible. And that's the one I use as a reference, because we expect it should be more or less like that. And with that, we have computed the inside metric. And what goes on, for instance, is that along the singularity itself, as you would imagine, the mass decreases because sort of negative Hawking quanta fall in. The Hawking quanta is, it's an intuitive thing, but it's not a very good thing either, because you might think that they're outgoing, but they're also ingoing. So they're neither one nor the other. So what I'm saying is that, yes, there is a back reaction, which is complicated. There are papers, if you send an email to me, I'll send you some calculations, but the problem is, it's very hard to give something definitive.
Thank you.
Thank you, Carlo. More questions? So I don't see any other raised hands. So then we are coming to the end. Let me thank all the speakers of this first part of our parallel session. Let me remind you that tomorrow at 6:30 a.m. we'll have the second the second part of our parallel session, I would like to invite all of you. Tomorrow is just in a couple of hours, I think. So we'll have 7 talks tomorrow morning, and also many interesting subjects regarding black hole thermodynamics. So thank you very much for your participation. Thank you very much all the speakers and for the interesting questions. And so thank you so much. See you tomorrow. Bye.
Thank you, Hernando.
See you. Bye. Thank you.
See you.